Hello and welcome. You are here to rest, and that is exactly what this time is for. There is nothing you need to do, nothing you need to figure out, and nothing you need to remember when this is over. You can simply let yourself be still, let your breathing slow down, and let the sound of a voice carry you gently towards sleep. This is a story about tiny things and patient people, a slow walk through the history of the atom's core, from ancient guesses to modern reactors. But it is not a lecture, and it is not a test. It is a quiet journey, the kind you can take with your eyes closed, drifting in and out of attention, catching a word here and a phrase there, and letting the rest wash past you like water. Think of this as a long, meandering path through a landscape of ideas. We will start a very long time ago, when people first began to wonder what the world was made of, and we will move forward slowly, century by century, discovery by discovery, until we arrive at the present day. Along the way, we will meet people who spent years staring at small, glowing screens, people who stirred heavy pots of boiling liquid, people who sat in quiet rooms and thought very hard about very small things. None of them were in a hurry, and neither are we. This is a story that unfolds at its own pace, and your only job is to let it unfold around you, without strain, without effort. The plan is loose and gentle. We will begin with the earliest guesses about matter, the kind of ideas that came to people who had no microscopes, no laboratories, no way of seeing anything smaller than a grain of sand. Then we will move into the time when real experiments began, when people first noticed strange behaviors in certain rocks and minerals, behaviors that hinted at something hidden deep inside the smallest pieces of the world. From there, we will trace the slow uncovering of the atom's interior, the discovery that atoms are mostly empty space with a tiny, dense center, and then the naming of the parts that make up that center. We will talk about how people learned to split that center apart, and how that knowledge changed the world in ways both large and small. We will talk about the sun and the stars and the way they burn, and we will talk about the unfinished work of bringing that same fire down to Earth. And finally, we will look a little deeper still, at the particles inside the particles, the layers within layers, and then we will let the whole picture settle back into stillness, the way a pebble settles to the bottom of a pond. But none of that needs to be held in your mind right now. You do not need to keep track of the order or the names or the dates. This is not a story that requires you to follow along carefully. It is more like a landscape you are passing through, and you can let your gaze drift from one part of it to another without worrying about the map. If you fall asleep halfway through a sentence, that is perfectly fine. If you wake up a few minutes later and hear words that seem to come from a different part of the story, that is also fine. The story will be here, moving along at its own slow pace, and you can dip into it or drift away from it as you please. The framing of this journey is calm. That is important to say up front. When people talk about the atom, they sometimes talk about danger, about bombs and radiation, and things that sound frightening. Those things are part of the history, and we will touch on them quietly as we go, but they are not the heart of the story. The heart of the story is curiosity, patience, and the slow accumulation of understanding over many lifetimes. The people we will meet were not action heroes. They were careful, methodical, often tired people who worked long hours in dimly lit rooms, who made mistakes and corrected them, who argued with each other in polite letters and at quiet conferences. Their work was slow, and our telling of it will be slow as well. There is no urgency here. The atom has been around for billions of years, and it will be around for billions more. There is plenty of time. What we are doing, really, is taking a very old question and following it forward through time. The question is simple. What are things made of? A rock, a leaf, a cup of water, a human hand. If you could cut them into smaller and smaller pieces, what would you find at the very bottom? Would there be a smallest piece at all, something that could not be cut any further? Or would the division go on forever, each piece containing still smaller pieces without end? This question has kept people company for a very long time, and just sitting with it, just turning it over in the mind, has a kind of quiet comfort to it. It is a question that does not demand an immediate answer. It is a question you can fall asleep to. By the time we reach the end of this journey, you will have heard about many things. You will have heard about protons and neutrons and electrons, about alpha particles and beta particles and gamma rays, about fission and fusion and chain reactions. You will have heard names like Democritus and Dalton and Rutherford and Curie and Fermi and Gell-Mann. But you will not need to remember any of them. In fact, the hope is that you do not try to remember them. The hope is that you let the words wash over you like sounds, like the rhythm of rain or the murmur of a distant river. The facts are not the point. The point is the feeling of being told a long, gentle story, the feeling of being accompanied into sleep by a voice that expects nothing from you. Think of it this way. When you were a child, and someone read you a bedtime story, you probably did not lie there memorizing the plot points and the character names. You let the sound of the reader's voice carry you, and you let the images float up in your mind, and eventually the words became a kind of music, and then the music faded, and then you were asleep. This is the same kind of experience, just for a grown-up mind that has learned a few more words and seen a few more things. The content is different, but the container is the same. A voice, a story, a slow descent into stillness. So let us begin that descent together. Let us take the first step onto this long, winding path. The air is cool and the light is low. There is no hurry. The story will take as long as it takes, and you are free to fall asleep at any point along the way. Nothing you miss will be lost, because nothing needs to be retained. The only thing that matters is that you are lying there, comfortable and warm, letting your body rest and your mind wander. The story is just a companion for that wandering, a gentle hand to hold in the dark. We are going to start with the very old days, the days when the question of what things are made of was still brand new. Before microscopes, before telescopes, before any instrument that could extend the reach of the human eye, people looked at the world and wondered. They saw water evaporate and rocks erode and wood burn to ash, and they asked themselves what was really happening underneath all that change. Was there something permanent, something that stayed the same while everything else shifted and transformed? Or was change the only reality, and permanence just an illusion? The ancient Greeks spent a lot of time on this kind of question. They did not have laboratories in the way we think of them today. They had minds, and they had conversation, and they had the long, slow hours of a world without clocks. They sat in the shade and talked, and they argued, and they proposed ideas, and then they proposed counter-ideas, and the whole thing unfolded like a very slow, very patient game. It is hard to imagine now, in a time when information moves so quickly, but for centuries, the main tool for investigating the nature of reality was simply thinking hard about it. And the thinking was often very good. One of the ideas that came out of that time was the idea that everything in the world might be made of tiny, invisible pieces that could not be cut any further. The Greek word for uncuttable was atomos, and that is where our word atom comes from. The person most often associated with this idea was a man named Democritus, who lived about 2,500 years ago. He and his teacher, Leucippus, proposed that if you took a piece of matter, a piece of wood, say, or a piece of metal, and you kept cutting it into smaller and smaller bits, you would eventually reach a piece so small that it could not be divided anymore. That smallest piece was the atomos, the indivisible thing. Now, this was not a scientific theory in the modern sense. Democritus did not do experiments. He did not build instruments. He looked at the world and he reasoned about it, and he came to a conclusion that felt satisfying to him. He imagined these tiny particles as being solid, eternal, and infinite in number, moving through empty space, colliding and combining to form all the different substances we see around us. The atoms of water were smooth and slippery, he thought, which is why water flows. The atoms of iron were rough and jagged, which is why iron holds together so strongly. The atoms of the soul were the finest and most mobile of all, which is why thought and feeling can move so quickly through us. It was a beautiful idea, elegant and complete, and it was almost entirely forgotten for a very long time. Other Greek thinkers, particularly Aristotle, argued against it, and Aristotle's views carried more weight for centuries. He believed that matter was continuous, not made of discrete particles, and that all substances were combinations of four elements: earth, air, fire, and water. That idea held sway for nearly 2,000 years. The atom of Democritus became a footnote, a curiosity, an interesting wrong turn in the history of thought. But the idea did not die completely. It slept, like a seed waiting for the right conditions. And those conditions began to arrive in the 1700s, when the tools of chemistry started to become more precise. People began to weigh things carefully, to measure how substances combined and separated, to look for patterns in the behavior of gases and liquids and solids. And the patterns they found pointed, slowly and insistently, toward the idea that matter really was made of discrete units after all. The person who brought the atom back into serious consideration was an English schoolteacher named John Dalton. In the early 1800s, Dalton was studying the behavior of gases, and he noticed something interesting. When elements combined to form compounds, they always did so in fixed ratios by weight. Water, for example, was always made of hydrogen and oxygen in the same proportions, no matter where the water came from or how it was formed. This suggested that the elements were combining as whole units, not as continuous substances that could mix in any proportion. If matter were continuous, you could mix hydrogen and oxygen in any ratio and get something like water. But that is not what happens. You get water only when the ratio is right, and any extra of either element is left over. Dalton proposed that each element was made of tiny, identical particles. He used the word atom, and that these atoms combined in simple, whole number ratios to form compounds. The atoms of a given element were all the same size and weight, he thought, and different from the atoms of any other element. This was a huge leap forward. It was no longer just a philosophical idea. It was a scientific hypothesis that made predictions you could test, and when people tested them, the predictions held up. Still, it is important to remember where we are in the story. This is the early 1800s. Dalton's atoms are solid, indivisible little spheres. No one has any idea that atoms have an inside at all. The word nucleus is not part of the conversation. The word electron has not been coined. Radioactivity is not even a glimmer on the horizon. For all anyone knows, the atom is the end of the line, the smallest possible piece of matter, exactly as Democritus imagined it 2,000 years earlier. And that is where we will leave things for now, with the atom as a tiny, solid, indivisible ball, the fundamental building block of all the world's substances. It is a tidy picture, a satisfying picture, and it will hold for a little while longer. But in the back of the story, in the quiet spaces between the chapters, a few strange observations are beginning to accumulate. Certain minerals are behaving oddly. Certain rocks are giving off a faint, persistent energy that no one can explain. The atom's smooth surface is about to be cracked open, and we will walk through that opening together when the time comes. But not yet. For now, the atom is whole, and the night is deep, and you can rest in that wholeness. Let the solid little spheres float in your mind, tiny and perfect and unbroken. There is nothing to do, nothing to hold on to. Just breathe, and let the story pause here, and drift. The solid little spheres of John Dalton were a good beginning. They explained a great deal. They explained why elements combine in fixed ratios, why chemical reactions behave as though they are rearranging whole units rather than blending continuous substances. For a long time, through the early and middle parts of the 1800s, this picture held. Atoms were the smallest possible pieces of matter, indivisible and eternal, exactly as Democritus had imagined them on a warm Greek afternoon more than 2,000 years before. It was a clean, orderly picture, and like many clean, orderly pictures, it was not quite complete. Let us go back further than Dalton, though, before we move forward. Let us sit for a while with those ancient Greek thinkers, because their story is worth telling slowly. It is a story about what happens when people have time to think, when there is no pressure to produce a result, when the only goal is to understand something a little better than before. That kind of thinking has a different texture than modern science. It is softer, more speculative, more like daydreaming, and since we are here to drift towards sleep, a little daydreaming is exactly right. Democritus was born in the city of Abdera, in northern Greece, around the year 460 before the Common Era. That is nearly 2,500 years ago. He lived a long life, perhaps into his 90s, and he wrote a great many books, though none of them survive in full. What we know of his ideas comes from later writers who quoted him, sometimes approvingly, sometimes not. He was known as the laughing philosopher, because he was said to find humor in the follies of humanity. There is something nice about that, something restful. The person who first proposed the atom was not a grim, severe figure. He was someone who looked at the world and found reasons to smile. Democritus and his teacher Leucippus, about whom we know very little, proposed that everything in the universe was made of two things, atoms and the void. The atoms were tiny, solid, indivisible particles, infinite in number and variety. The void was the empty space in which they moved. The atoms were always in motion, colliding with one another, sticking together, breaking apart, forming new combinations. All the changes we see in the world, the growth of plants, the flow of water, the hardening of clay, the birth and death of living things, were the result of atoms rearranging themselves. The atoms themselves were eternal. They were never created and they were never destroyed. They simply changed partners, the way dancers might form new pairs when the music shifts. This idea did not come from nowhere. It was a response to a philosophical problem that had been troubling Greek thinkers for some time. The problem was about change. How can something change and still be itself? If a tree grows from a seed, is the tree the same thing as the seed? If you eat bread and the bread becomes part of your body, how does that happen? What stays the same and what becomes different? The atomists had an elegant answer. The atoms stay the same. They are the permanent, unchanging substrate. The arrangements change. The combinations come and go. But the fundamental pieces, the atoms themselves, are constant. It is important to say and say again that this was not based on experiment. There was no way in ancient Greece to see an atom or to measure one. The idea was purely a product of reasoning, of thinking through the logical implications of a few basic assumptions. If you cut a piece of matter in half, and then in half again, can you keep going forever? The atomists said no. There must be a limit, a smallest piece that cannot be divided further. If there were no limit, they argued, then matter would be infinitely divisible, and that led to logical problems they found hard to accept. So they drew a line, and they called the smallest piece atomos, which means uncuttable. The idea had a certain power, a certain elegance. It explained a lot with very little, but it did not win the day. Aristotle, who came a generation or two later, rejected the atomic theory. He preferred a different picture, one in which all matter was made of four elements: earth, air, fire, and water. These elements could transform into one another, and they were continuous, not made of discrete particles. Aristotle's view became the dominant one, and it stayed dominant for nearly 2,000 years. The atomic theory did not disappear entirely. It was kept alive by a few writers, notably the Roman poet Lucretius, who wrote a long poem called On the Nature of Things that explained the atomic theory in beautiful, flowing verse. But for the most part, the idea of the atom went to sleep. It was a seed planted in the soil of Western thought, waiting for conditions to change. Those conditions began to change in the 1700s, with the rise of modern chemistry. People started to weigh things precisely. They started to measure how much of one substance combined with how much of another. They found patterns, regularities, laws. and those laws pointed little by little back toward the atom. John Dalton, the English school teacher we met briefly at the end of the last section, was not the first person to revive the atomic idea, but he was the one who made it stick. He was a quiet, methodical man, a Quaker who spent his days teaching and his evenings doing experiments. He was interested in gases, in weather, in the behavior of air and water vapor, and he was interested in the patterns he saw when elements combined to form compounds. Dalton noticed that when two elements combine to form more than one compound, the weights of one element that combine with a fixed weight of the other are always in simple, whole number ratios. This is a bit of a mouthful, so let us take it slowly. Imagine you have carbon and oxygen. They can combine to form carbon monoxide or carbon dioxide. In carbon monoxide, a certain weight of carbon combines with a certain weight of oxygen. In carbon dioxide, the same weight of carbon combines with exactly twice as much oxygen, not 1.7 times as much, not 1.9 times as much. Exactly twice. This kind of simple ratio kept showing up, over and over, across many different elements and compounds. Dalton reasoned that this made sense if each element was made of tiny, identical particles that combined in whole numbers. One atom of carbon combines with one atom of oxygen to make carbon monoxide. One atom of carbon combines with two atoms of oxygen to make carbon dioxide. The simple ratios were a natural consequence of the atomic structure. If matter were continuous, you would not expect such clean, whole number relationships. You would expect smooth, gradual variation. The fact that the ratios were sharp and simple was a strong hint that matter came in discrete units. Dalton proposed his atomic theory in the early 1800s. He suggested that all matter is made of atoms, that atoms of a given element are all identical in size and weight, that atoms of different elements have different sizes and weights, and that chemical reactions rearrange atoms without creating or destroying them. He even drew up a table of atomic weights, estimating the relative masses of the atoms of different elements. His estimates were not all accurate, but the framework was sound. The atom was back. Still, it is worth pausing here to emphasize something. Dalton's atoms were still the atoms of Democritus in one crucial respect. They were solid, indivisible, and without internal structure. Dalton had no concept of a nucleus. He had no concept of electrons orbiting that nucleus. He had no concept of protons or neutrons or any of the other particles we will meet later in this story. For Dalton, the atom was the end of the line. It was the smallest thing. It had no parts. It was a tiny, featureless sphere, and that was that. This picture held for most of the 19th century. Chemists used it to great effect. They classified elements, they predicted new ones, they built an entire science on the foundation of these tiny, indivisible spheres. But even as the atomic theory was proving its worth, hints were beginning to appear that the atom was not the end of the story after all. There were observations that did not quite fit, phenomena that the simple solid sphere model could not explain. One of these hints came from the study of electricity. When scientists passed electric currents through glass tubes from which most of the air had been pumped out, they saw strange glows, strange rays. These were called cathode rays, and their nature was a subject of intense debate. Were they waves? Were they particles? Something else entirely? The debate went on for decades, and we will not go deeply into it now, but it is enough to know that these cathode rays were eventually identified as streams of tiny, negatively charged particles, particles much smaller than atoms. They were given the name electrons. This was the first real crack in the idea of the atom as indivisible. If atoms contained smaller particles, then they were not the smallest things after all. Another hint came from the study of light. When certain elements were heated until they glowed, they did not emit a smooth, continuous spectrum of colors. They emitted light only at very specific wavelengths, sharp, bright lines of color against a dark background. Each element had its own unique pattern of lines, like a fingerprint. This was useful for identifying elements, but it was also deeply puzzling. Why should an atom emit light only at certain wavelengths? The solid sphere model had nothing to say about this. It suggested that something inside the atom was structured in a very particular way, that it could exist only in certain states and not in others. But what that structure might be was still a complete mystery. And then there were the strange minerals, the ones we mentioned at the end of the last section. Certain rocks, particularly those containing uranium, seemed to give off a kind of energy. They fogged photographic plates. They made the air around them conduct electricity. They glowed faintly in the dark. This energy did not seem to come from any external source. It was not caused by heating or by chemical reaction. It came from within the atoms themselves. This was perhaps the most profound hint of all, because it suggested that atoms were not just structured, they were active, they were doing something, and that something was about to change everything. But we are not ready to go there yet. We are still in the early 1800s, or perhaps the middle of the century, and the atom is still a simple, solid ball. The discoveries that will open it up are still decades away. For now, let us stay with the idea of smallness a little longer. Let us sit with the notion that everything we see, everything we touch, everything we are, is made of pieces so tiny that no one has ever seen them directly. Even today, with all our instruments and all our technology, no one has ever seen an atom with the naked eye. They are too small. A single grain of sand contains more atoms than there are stars in the observable universe. That is a difficult thought to hold on to, but it is a soothing one too. It means that the world is deeper and stranger than it appears. It means that there is always more to discover, always another layer beneath the one we can see. The ancient Greeks understood this in their own way. Democritus and his followers looked at the world and saw the invisible dance of atoms. They saw a universe made of tiny, eternal pieces, moving through endless space, combining and recombining in an infinite variety of forms. It was a vision of extraordinary beauty, and it came from nothing more than careful thought. No microscopes, no particle accelerators, no photographic plates. Just a mind, a long afternoon, and the willingness to follow a question wherever it led. Now, as we lie here in the dark, we can follow that same question. We can let our minds drift back to a time when the smallest things were still a complete mystery, when the nature of matter was an open question, when the word atom was a philosophical speculation rather than a scientific fact. We can imagine the laughing philosopher, Democritus, walking through the streets of Abdera, turning over his ideas in his mind, not knowing that his speculation would one day be confirmed in ways he could never have imagined. We can imagine John Dalton in his quiet study, weighing his samples, recording his measurements, building the atomic theory piece by piece from the ground up. These were patient people. They worked slowly. They did not expect quick answers. They were content to move forward one small step at a time, and that contentment is something we can share, here in the dark, as we let the story carry us along. The atom is still a solid ball for now. But not for much longer. The 19th century is drawing to a close, and a French physicist named Henri Becquerel is about to make a discovery entirely by accident. He will leave some uranium salts on a photographic plate, wrapped in black paper, in a drawer. He will expect nothing to happen, and the plate will be fogged when he develops it. The atom will begin to show its hidden structure, and we will be there to see it. But that is for the next part of the story. For now, just let the atoms float, tiny and whole and unbroken, in the vast empty space that makes up everything. Let them drift in your mind like dust motes in a sunbeam, slowly settling, slowly coming to rest. The story will continue when you are ready. For now, there is only stillness and the quiet dance of things too small to see. The accidental discovery of radioactivity is a story about cloudy weather and a closed drawer. It is a story about what happens when a careful person notices something small, something that would be easy to overlook, something that was not part of the plan. and it is a story that begins in Paris, in the last years of the 19th century, at a time when the atom was still thought to be a solid, unchanging ball. Henri Becquerel was a physicist, the third in a line of scientists in his family. His grandfather had studied electricity. His father had studied light and phosphorescence, the way certain materials glow for a while after they have been exposed to sunlight. Henri carried on this family interest. He kept a collection of minerals and salts that were known to glow in the dark after being placed in the sun, and he was curious about whether this glow might include a new kind of ray, something like the X-rays that had been discovered by Wilhelm Röntgen just a few months earlier, in 1895. The discovery of X-rays had caused a great stir. For the first time, people could see inside a living body without cutting it open. The rays passed through soft tissue, but were blocked by bone, leaving a shadow image on a photographic plate. It seemed like magic, though it was physics. Scientists all over the world were looking for other sources of invisible rays. Becquerel wondered whether the phosphorescent minerals he had been studying might also give off rays that could pass through solid objects and expose a photographic plate. His experiment was simple. He would take a photographic plate, wrap it in thick black paper so that no ordinary light could reach it, and place a sample of a phosphorescent mineral on top of the wrapped plate. Then he would set the whole arrangement in sunlight for several hours. The sunlight would charge up the phosphorescent material, making it glow. If that glow included penetrating rays like X-rays, the rays would pass through the black paper and fog the plate underneath. When he developed the plate, he would see a dark spot where the mineral had been sitting. He tried this with several different minerals, and he got results. Some of them did seem to produce rays that could penetrate the paper, but one mineral in particular caught his attention. It was a salt of uranium, a heavy, metallic element that had been known since the late 1700s. Uranium was not particularly rare, but it was not much used for anything. Its salts were bright yellow and were sometimes used to color glass and ceramics. Becquerel found that uranium salts produced a much stronger effect on his photographic plates than any of the other phosphorescent materials he tested. The spots on the developed plates were darker, sharper, more distinct. He planned to continue these experiments, to refine his understanding of how the effect depended on the amount of sunlight, the type of mineral, the length of exposure. Science often proceeds this way, in small steps, each experiment suggesting the next one. But the weather in Paris did not cooperate. For several days, the sky was overcast. The sun did not come out. Becquerel could not charge up his phosphorescent minerals because there was no sunlight to charge them with. So he put his prepared plates and his mineral samples in a drawer and waited. This is the part of the story where the accidental discovery happens. Becquerel had a photographic plate wrapped in black paper with a uranium salt sample resting on top of it. The whole thing was sitting in a dark drawer. No sunlight had touched it. The uranium had not been charged up. It was not glowing. By the logic of his experiment, nothing should have happened. The plate should have remained unexposed. And yet, for some reason he could not fully explain, Becquerel decided to develop that plate anyway. What he saw was a surprise. The plate was fogged. It showed a dark, distinct shadow of the uranium sample, just as sharp as if the mineral had been sitting in bright sunlight for hours. But it had not been. It had been sitting in a dark drawer, wrapped in black paper, doing nothing, or so he had thought. This was the moment when the atom's smooth surface began to crack. The energy that fogged the plate was not coming from the sun. It was not coming from any external source. It was coming from the uranium itself. The atoms of uranium were giving off some kind of invisible ray, continuously, without being stimulated or charged or heated. They were doing it all on their own, in the dark, quietly and steadily, for no apparent reason. Becquerel had discovered what we now call radioactivity, though the word itself had not been coined yet. He had found the first evidence that atoms were not just tiny, solid, indivisible balls. They were active. They were capable of emitting energy. Something was going on inside them, something that the simple Dalton model could not account for. The discovery was announced in 1896, and it opened a door that would never be closed again. Let us pause here for a moment and sit with the scene. Imagine a laboratory in Paris. Late winter, the light gray and dim through the windows. The room is not large. There are wooden tables, glass beakers, photographic plates stacked in boxes. There is the faint chemical smell of developing fluid. Becquerel is a quiet man, methodical, carrying on the family tradition of careful inquiry. He is not in a hurry. He is not expecting to change the world. He is following a question, the way a person might follow a path through a forest, not knowing exactly where it leads, but trusting the ground underfoot. He develops the plate, and the image appears, a dark spot, a shadow of something that should not have cast a shadow. He does not shout or call for his colleagues. He stands there, looking at the plate, turning over the implications in his mind. The uranium has done something it should not have been able to do. The atom, which was supposed to be the smallest, most stable, most unchanging thing in the universe, has spontaneously emitted energy. The solid little ball is not so solid after all. Becquerel published his findings. The scientific world took notice, but it was two other scientists, working in the same city, who would take the discovery and push it forward into entirely new territory. Their names were Marie and Pierre Curie. Marie Curie was born Maria Sklodowska in Warsaw, Poland, in 1867. She came to Paris to study at the Sorbonne, one of the few places in Europe where women could pursue advanced scientific education at that time. She lived in a cold attic room, studied late into the night, and earned degrees in physics and mathematics. She met Pierre Curie, a quiet, gentle physicist who had already done important work on crystals and magnetism, and they married in 1895. They began working together, sharing a laboratory and a life. When Becquerel announced his discovery of uranium's strange rays, Marie Curie decided to investigate further. She was looking for a subject for her doctoral thesis, and this was a field that was wide open. No one knew what these rays were, or where they came from, or whether other elements besides uranium produced them. She began to test every element and mineral she could find, using sensitive instruments that her husband Pierre had helped design. These instruments measured the ability of the rays to make air conduct electricity, which was a more precise method than waiting for photographic plates to fog. She found something important very quickly. Uranium was not the only element that gave off these rays. Thorium, another heavy metal, did as well, and the amount of radiation given off by a sample did not depend on its chemical form, or its temperature, or whether it was in a pure state or combined with other elements. It depended only on the amount of the active element present. This was a crucial clue. It meant the radiation was not a chemical property, not something that came from the way atoms were arranged in molecules. It was an atomic property. It came from the atoms themselves, from deep inside them. Marie Curie gave this phenomenon a name. She called it radioactivity, from the Latin word radius, meaning ray. It was a new word for a new kind of behavior, one that had no place in the existing understanding of matter. Radioactivity was not like burning or rusting or any other chemical reaction. It was not affected by heat or cold or pressure. It went on steadily, no matter what. An atom of uranium or thorium would sit quietly and emit its rays, second after second, minute after minute, day after day, and nothing you could do would speed it up or slow it down. As Marie Curie continued her measurements, she noticed something else. Some of the minerals she tested gave off more radioactivity than they should have, based on the amount of uranium or thorium they contained. Pitchblende, a dark, heavy ore from which uranium was extracted, was several times more radioactive than pure uranium itself. This made no sense unless the ore contained something else, some other element that was far more radioactive than uranium, but present in very small amounts. This was the clue that led to the great labor of the Curie's life together. They decided to try to isolate the unknown element, the thing in the pitchblende that was producing the extra radiation. They knew it would be difficult. The substance they were looking for was present in tiny quantities, mixed in with tons of raw ore. They would have to process enormous amounts of material, grinding it, dissolving it, filtering it, boiling it down, all to extract a fraction of a gram of the mystery element. It was a huge undertaking for a husband and wife working in a makeshift laboratory with very little money. Their workspace was an old shed, formerly used for dissecting bodies at the School of Physics and Chemistry in Paris. It was damp, poorly ventilated, freezing in winter and stifling in summer. The floor was bare earth. The roof leaked. There were no hoods to carry away fumes. The Curies worked there for 4 years, from 1898 to 1902, processing tons of pitchblende by hand. Marie Curie described it later as a kind of joyful labor. They were young, they were in love, and they were doing work that mattered to them. The exhaustion was real, but so was the satisfaction. They worked systematically. First, they separated the pitchblende into its known chemical components. Then they tested each fraction for radioactivity, keeping the active portions and discarding the rest. Slowly, painstakingly, they narrowed down the source of the radiation. They found that it was concentrated in 2 different chemical fractions, meaning there were likely 2 different new elements, not just one. In July of 1898, they announced the discovery of the first new element. Marie named it polonium, after her native Poland. It was intensely radioactive, far more so than uranium, but it was present in vanishingly small amounts. Later that same year, in December, they announced the second element. They named it radium, from the Latin word for ray. Radium was even more radioactive than polonium, and it glowed with a faint, beautiful blue-green light in the dark. The Curies worked for 4 more years to produce enough pure radium to measure its atomic weight. The amount they finally isolated was tiny, about 1/10 of a gram, but it was enough to confirm the element's identity. The physical toll of this work was significant, and we can state it plainly, without drama. The shed where they worked had no ventilation. They breathed in fumes. They handled radioactive materials with bare hands. Their fingers became cracked and sore. Pierre Curie deliberately exposed a patch of his own skin to radium to see what would happen. It produced a burn that took weeks to heal. The dangers of radioactivity were not yet understood. The Curies knew that their materials gave off energy, but they did not fully grasp the damage that energy could do to living tissue. Marie Curie carried vials of radium salts in her pockets. She kept a small sample by her bedside because she liked the glow. Years later, her notebooks and even her cookbook would be too radioactive to handle without protective gear. The work shortened their lives. Pierre Curie died in a street accident in 1906, killed by a horse-drawn cart on a rainy Paris street. Marie lived until 1934, but she suffered from chronic illness, almost certainly caused by her long exposure to radiation. All of this was in the future, unknown and unsuspected, as they stood in their shed and watched the faint glow of radium in the dark. For now, the discovery was pure. The atom was no longer a solid, inert ball. It was a source of energy, a tiny engine running for reasons no one yet understood. We will leave the Curies here, with their purified samples and their aching hands, and let the significance of their work settle into the quiet of the room. They had found something fundamental. They had shown that atoms could transform themselves, that they were not the eternal, unchanging particles of Democritus and Dalton. Something inside the atom was unstable. Something inside it could break apart, releasing energy. What that something was, and how it worked, would take decades more to understand. But the first crack had been made. The hidden interior of the atom was beginning to show itself. In the next part of the story, we will meet a man named Ernest Rutherford, who will take these new rays and begin to sort them out. He will give them names, he will measure their properties, and he will use them as tools to probe even deeper into the structure of the atom. But that is for later. For now, let the image rest in your mind. A dark shed in Paris, a faint blue-green glow, and 2 people working quietly together. not knowing where their discoveries would lead. Let the glow fade slowly, like the last ember in a fireplace, and let the darkness gather around it. The story is in no hurry, and neither are you. Ernest Rutherford was a big man with a big voice and a big personality. He was born on a farm in New Zealand, far from the great scientific centers of Europe, and he never lost the plain-spoken, practical manner of his upbringing. He once said that all science is either physics or stamp collecting, a gentle joke that tells you something about his direct, no-nonsense approach to the world. He was not a man for complicated theories or elaborate speculations. He liked experiments that gave clear answers, experiments you could hold in your hand and understand. Rutherford arrived in England in 1895, the same year Röntgen discovered X-rays, and the year before Becquerel found the strange rays from uranium. He was 24 years old, a scholarship student from the far side of the world, and he was ready to work. He fell into the study of radioactivity almost immediately. It was the most exciting thing happening in physics, a field wide open for someone with patience and clever hands. The Curies had shown that certain elements gave off rays. Becquerel had shown that uranium did it whether the sun was shining or not. But nobody knew what these rays were. Were they particles? Were they waves? Were they all the same kind of thing? Or was there more than one type? Rutherford set out to answer these questions, and he began by doing something very simple. He took a sample of uranium and he put it near a detector. Then he placed different materials between the uranium and the detector to see what would happen. What he found was that the radiation from uranium was not a single thing. Some of it was stopped very easily. A thin sheet of paper, or even a few centimeters of air, was enough to block it completely. This kind of radiation could not travel far at all. It was easily absorbed. Rutherford named this type of radiation alpha, after the first letter of the Greek alphabet. The name did not mean anything in particular. It was simply a label, a way of saying the first kind. But there was another type of radiation coming from the uranium, and this second type behaved quite differently. It was much more penetrating. It could pass through paper easily. It could pass through thin sheets of metal. It could travel through air for a much greater distance than the alpha radiation. Rutherford named this second type beta, after the second letter of the Greek alphabet. Again, the name was just a label, a way of keeping things organized. So Rutherford had identified two kinds of radiation, two different ways that a uranium atom could shed energy. One was heavy and slow and easily stopped. The other was lighter and faster and more penetrating. He did not yet know what they were made of. That would come later, as more experiments were done. But simply sorting the radiation into two categories was a big step forward. It brought order to a confusing picture. It gave people a way to talk about what they were seeing. Let us sit with these two types of radiation for a moment, because the classification itself is restful. There is something calming about sorting things, about putting them into neat categories, about giving names to what was previously vague and undefined. Alpha and beta, two Greek letters, two ways of being radioactive, one that barely makes it across the room, one that can slip through solid matter like light through a window. Both coming from the same lump of uranium, quietly, steadily, without any fuss. The alpha radiation, as Rutherford eventually determined, is made of particles that are relatively large and heavy. Each alpha particle is, in fact, a small cluster of protons and neutrons, the same as the nucleus of a helium atom. Because it is relatively large and carries an electric charge, it interacts strongly with other atoms as it travels. It bumps into them, knocks electrons loose, and quickly loses its energy. That is why a sheet of paper stops it. That is why a few centimeters of air stop it. It is a blunt, heavy thing, easily blocked. The beta radiation is different. Beta particles are much smaller and much faster. They are, in fact, electrons, the same tiny, negatively charged particles that orbit the nucleus of an atom. Because they are so small and so fast, they can slip past other atoms more easily. They do not bump into things as readily. They can travel through paper and through thin metal. They are stopped eventually by thicker materials, but they penetrate much further than alpha particles do. So we have two types of radiation, alpha and beta, one heavy and one light, one easily stopped and one more penetrating. This was a tidy picture, and it held for a few years. But then a third type of radiation was discovered, and it was even more penetrating still. The discovery of the third type came from a French physicist named Paul Villard, working in Paris around 1900. Villard was studying the radiation from radium, the element the Curies had isolated with such difficulty. He noticed that even when he blocked both the alpha and the beta radiation, there was still something getting through. A third kind of ray, one that was not deflected by magnets, one that was not made of charged particles at all. This third kind of ray could pass through thick metal plates. It could pass through materials that stopped beta particles easily. It was, in a sense, the most penetrating radiation of all. Rutherford, following his orderly habit, gave this third type a name. He called it gamma, the third letter of the Greek alphabet. Gamma rays, he eventually showed, were not particles at all in the way alpha and beta were. They were a form of light, but light of a very particular kind. Ordinary light, the kind we see with our eyes, has a certain amount of energy. Gamma rays have much more energy per packet of light. They are, in a sense, extremely energetic light waves, or light particles, so energetic that they can pass right through most solid matter, the way ordinary light passes through clear glass. So now we have three types: alpha, beta, gamma. 3 letters, 3 ways an atom can release energy. They differ in size, in speed, in penetrating power. They differ in what they are made of, but they all come from the same source. They all come from the tiny, unstable core of an atom that is trying to settle into a more stable state. Think of it this way. Some atoms, like uranium or radium, have cores that are not quite stable. They are a bit like a ball sitting on a slope. The ball wants to roll down to the bottom, where the ground is level, and it can come to rest. But it is stuck, for now, partway up the slope. The act of emitting radiation is the ball rolling a little further down. The alpha or beta or gamma ray is the energy the ball releases as it moves. After the emission, the atom's core is a little more stable than it was before. Sometimes it takes more than one step to reach the bottom. Sometimes an atom emits an alpha particle, and then a beta particle, and then a gamma ray, each one moving the core closer to stability, like a ball bumping down a slope one ledge at a time. This is a gentle way of thinking about radioactivity. It is not a violent explosion. It is a slow settling. It is an atom rearranging itself into a more comfortable shape, releasing the extra energy it does not need. The energy itself can be harmful to living things, as the Curies learned in their own bodies, but the process by which it is released is quiet, patient, and inexorable. The atom does not hurry. It takes as long as it takes. For some elements, the process takes billions of years. For others, it takes a fraction of a second. But it always follows the same rules, and it always moves towards stability. Rutherford's classification of alpha, beta, and gamma radiation was a great help to the scientific community. It gave everyone a common language. It organized the chaos of early radioactivity research into something manageable. But Rutherford was not content just to name things. He wanted to know what the atom looked like inside, and he realized, with a flash of practical insight, that he could use the alpha particles themselves as a tool. He could fire them at other atoms and see what happened. He could use them as tiny probes, tiny bullets, to feel out the shape of the atom's interior. That is where we are heading next. The gold foil experiment, and the discovery of the empty atom. But we are not quite ready to go there. For now, let us stay with the 3 types of radiation a little longer. Let us roll their names around in our minds, slowly and softly, like smooth stones in the palm of a hand. Alpha, the heavy one, stopped by paper. A cluster of protons and neutrons, a helium nucleus in flight. It does not get far. It throws its weight around for a few centimeters, and then it comes to rest, its energy spent, its journey done. Beta, the light one, an electron fast and small. It slips through paper and thin metal. It travels further, penetrates deeper, but it is stopped eventually too. Thick aluminum, a sheet of plastic, a layer of clothing. It does not go on forever. Gamma, the weightless one, pure energy, light with no rest mass. It passes through almost everything: thick lead, meters of concrete, the human body, the air, the empty space between the stars. It is the most penetrating of the three, and it will travel until it hits something dense enough to absorb it. 3 ways of shedding energy, 3 ways for an atom to move toward rest. The names are simple and orderly, and there is something restful about that order. Alpha, beta, gamma, the first 3 letters of the Greek alphabet. 3 categories into which all of radioactivity, in its endless variety, can be sorted. Rutherford did this sorting in the early years of the 20th century, working in laboratories in Canada and then in England. He was a professor by then, a respected figure, with students and colleagues and a growing reputation, but he still worked with his hands. He still designed his own experiments. He still got excited when a new result came in, when a detector clicked or a screen flashed. He was a man who loved the work, and that love comes through in his letters, in the accounts of his students, in the way he talked about physics as a kind of play. The study of radioactivity was, in those early days, a study of things that could not be seen. No one had ever looked at an atom directly. No one had ever watched an alpha particle leave a nucleus. All the work was indirect. You set up an experiment. You watched a detector. You counted clicks or measured currents or developed photographic plates, and from these indirect traces, you built up a picture of what must be happening. It was like trying to understand the shape of an invisible object by throwing pebbles at it and listening to the sound they made when they hit. It required patience and imagination and a willingness to be wrong. Rutherford had all of these qualities. He was patient, he was imaginative in a practical, grounded way, and he was willing to be wrong. He changed his mind more than once over the course of his career, as new evidence came in. That is what good scientists do. They hold their ideas lightly. They let the evidence lead them, even when it leads them in directions they did not expect. The discovery of the 3 types of radiation was one step on a long path. It cleared the ground. It gave names to things that had been nameless. It allowed scientists to talk to one another with clarity, and it set the stage for what came next, which was the first real glimpse of the atom's interior. Imagine, as you lie here in the dark, the 3 rays spreading outward from a tiny point. Imagine alpha particles, heavy and slow, barely making it across the room before they come to rest. Imagine beta particles, faster and lighter, slipping through the air, through walls, through the space between objects. Imagine gamma rays, weightless and silent, passing through everything, a faint, invisible light that never stops. All of this is happening all the time, all around us, a quiet background hum of radioactivity that has been here since the Earth was formed. We do not feel it, we do not see it, but it is there, the gentle settling of atoms that have not yet found their final stability. The names are simple: alpha, beta, gamma. They are just labels, but they are labels that have lasted. More than a century later, we still use them. We still sort radiation into these same 3 categories, though we now know much more about each one. The clarity of Rutherford's thinking has stood the test of time, and Rutherford himself was not done. He had named the rays, now he was going to use them. He was going to take those heavy, slow alpha particles and aim them at a sheet of gold. He was going to watch what happened, and what he saw would change everything. But that is a story for the next quiet hour, the next slow chapter in our journey. For now, let the 3 Greek letters drift through your mind, soft and weightless as the rays they name: alpha, beta, gamma, 3 keys to a door that was just beginning to open. Let them fade now, one by one, as you sink a little deeper into the pillow. The story will be here when you are ready. There is no hurry. There is never any hurry. Just rest. The experiment that revealed the empty atom took place in Manchester, England, in the year 1909. It was a grey industrial city, full of factories and smoke and the sound of machinery. But inside the physics laboratory at the university, the work was quiet, precise, and slow. Ernest Rutherford was the professor there, and he had gathered around him a team of young researchers, men in their 20s mostly, eager to make their mark. 2 of those young men were Hans Geiger and Ernest Marsden. Their names would become attached to one of the most important experiments in the history of science, though they did not know that at the time. They were simply doing a job, following instructions, counting tiny flashes of light in a darkened room. The setup was simple in concept. Rutherford had a source of alpha particles, those heavy, positively charged fragments that we talked about earlier. The alpha particles came from a small amount of radium, the element the Curies had isolated with such difficulty. Radium emits alpha particles steadily, reliably, one after another, like a clock ticking. Rutherford's idea was to take a narrow beam of these alpha particles and aim it at a very thin sheet of gold foil. Gold can be hammered into sheets of extraordinary thinness, only a few hundred atoms thick. It is soft and workable, and it can be made so thin that light passes through it with a greenish tint. This thin gold foil was the target. The question Rutherford wanted to answer was a simple one. What happens when an alpha particle hits an atom? At the time, the prevailing model of the atom was something called the plum pudding model, proposed by J.J. Thomson, the man who had discovered the electron. In this model, the atom was a soft, spongy ball of positive charge, with the negatively charged electrons stuck into it, like raisins in a pudding or plums in a cake. It was a friendly, diffuse picture. There was nothing hard or dense about it. The positive charge was spread out evenly, like a fog, and the electrons floated inside it. If the plum pudding model was correct, then firing alpha particles at a thin gold foil should produce a predictable result. The alpha particles, which were relatively heavy and fast, should pass straight through the soft, diffuse atoms with only slight deflections. They might be nudged a little to one side or the other by the positive fog, but they should not bounce back. They should not be turned sharply around. There was nothing in the plum pudding atom dense enough or heavy enough to cause that kind of rebound. Rutherford asked Geiger and Marsden to test this. The experiment required patience. The alpha particles were detected by letting them strike a small screen coated with a material called zinc sulfide. When an alpha particle hits zinc sulfide, it produces a tiny flash of light, a scintillation. To see these flashes, you had to sit in complete darkness for at least half an hour, to let your eyes adjust to the dark. Then you looked through a microscope at the screen and counted the flashes, one by one, for hours at a time. It was tedious work. It required concentration and stillness, and a willingness to sit in the dark for long periods, watching for pinpricks of light. Geiger and Marsden did this. They counted the alpha particles that passed straight through the gold foil. They counted the ones that were deflected at small angles. And then, following a suggestion from Rutherford, they decided to check whether any alpha particles were bouncing back. They set up a screen on the same side of the foil as the alpha source, so that any particle that rebounded from the foil would hit the screen and make a flash. They did not expect to see much. According to the plum pudding model, there should be nothing in the atom that could turn an alpha particle around. But they did see flashes. A few alpha particles, a very small number, were bouncing back from the foil. They were being deflected through large angles, sometimes almost straight back toward the source. This made no sense in the context of the plum pudding model. It was, as Rutherford later put it, as surprising as if you fired a large artillery shell at a piece of tissue paper and it bounced back and hit you. Tissue paper does not bounce artillery shells. A soft, diffuse atom should not bounce alpha particles. Something was wrong with the model. Rutherford thought about this result for a long time. He did not rush to publish. He turned the problem over in his mind, considering different possibilities, different geometries, different ways of arranging charge and mass inside the atom. And eventually he arrived at a conclusion that was both simple and radical. The atom was not a soft, spongy ball. It was mostly empty space. The positive charge, and almost all of the mass, was concentrated in a tiny, dense core at the center. Rutherford called this core the nucleus, from the Latin word for a little nut or kernel. In this new picture, the nucleus was incredibly small compared to the atom as a whole. If you could enlarge an atom to the size of a large cathedral, the nucleus would be about the size of a fly in the middle of that cathedral. All the rest of the space was occupied only by the very light, negatively charged electrons orbiting at a great distance. The atom was not a plum pudding. It was more like a miniature solar system with a heavy central sun and tiny planets wheeling around it in the void. This explained the gold foil experiment perfectly. Most of the alpha particles passed straight through the foil because they were traveling through empty space, the vast empty regions between the tiny nuclei of the gold atoms. The nuclei were so small and so far apart that the chance of a direct hit was very small. But when an alpha particle did happen to approach close to a nucleus, the intense positive charge concentrated there repelled it strongly. The alpha particle, being also positively charged, was pushed away with great force. If it hit nearly head-on, it could be turned almost completely around. This was why a few alpha particles bounced back. They had encountered the fly in the cathedral. They had struck the tiny, dense core of the atom. Let us sit with this image for a while, because it is one of the central images of our whole story. The atom is mostly empty space. The solid objects around us, the chair beneath you, the floor, the walls, the body lying still under the blankets, are all made of atoms that are almost entirely void. The reason things feel solid is not because the atoms are solid. It is because the electric forces between atoms are strong enough to resist pushing. When you press your hand against a table, the electrons in your hand are repelled by the electrons in the table. The atoms themselves do not touch in the way we normally think of touching. They interact at a distance, through electric fields. The solidity of the world is a kind of illusion, a side effect of electromagnetism. Underneath that illusion, everything is mostly empty space, with tiny, dense nuclei scattered through it like dust motes in an enormous hall. Rutherford's model of the atom was a huge advance, but it was not the final word. It had problems that became apparent only later. One problem was that according to the laws of classical electromagnetism, an electron orbiting a nucleus should radiate energy and spiral inward. The atom should collapse in a fraction of a second. It obviously does not, but Rutherford's model could not explain why. The explanation would come from a new kind of physics called quantum mechanics, which was developed over the next 2 decades by Niels Bohr and Werner Heisenberg and Erwin Schrödinger and others. But that is another story, a story for a different quiet night. For now, we are focused on the nucleus, that tiny dense core, and how it came to be understood. The gold foil experiment was a turning point. It was the moment when the atom's interior came into view, not as a vague fog of charge, but as a structured object with a hard, heavy center and a vast, empty outer region. The nucleus had been discovered. The word nucleus entered the vocabulary of physics, and the next task was to understand what the nucleus itself was made of. But before we move on, let us linger a little longer with Geiger and Marsden in their dark room. Imagine the scene. The laboratory is quiet, the windows are blacked out. The 2 young men sit on wooden stools, their eyes adapted to the darkness, their faces lit only by the faint green glow of the zinc sulfide screen. They hear the ticking of a clock somewhere in the building. They smell the faint odor of chemicals, the dust of old wood, the wool of their suits. They take turns at the microscope, one counting while the other rests, then switching. The flashes they are counting are tiny, faint, like the briefest glimmer of a distant star. Most of the time they see nothing. The screen is dark. Then, a pinpoint of light, there and gone in an instant. A single alpha particle, announcing its arrival. They count for hours. They write numbers in a notebook. They shift the screen to a new position and count again. The work is repetitive, almost meditative. There is a rhythm to it, a kind of calm. They are not thinking about the implications of what they are doing. They are not imagining the Nobel Prizes that will eventually be awarded for this work. They are just counting flashes, one by one, in the dark. And then they move the screen to the other side of the foil, the side that should show nothing, and they see flashes there too, a few, very few, compared to the number that pass straight through, but unmistakably there, alpha particles bouncing back, the plum pudding model dissolving in the dark. Rutherford's quote about the artillery shell and the tissue paper is famous, and it captures the surprise of the moment perfectly. It is worth repeating because it is such a plain, vivid way of expressing something profound. A large shell bouncing off tissue paper. That is how unexpected the result was. It meant that the atom was not what anyone had thought. It meant that matter was not what it seemed. It meant that the solid world was built on a foundation of almost nothing. This is a restful thought, if you let it be. The idea that everything is mostly empty space can feel unsettling at first, but it can also feel liberating. The hardness of the world, the weight of things, the pressure of daily life, all of it is made of atoms that are themselves made of almost nothing. The dense core at the center of each atom is so tiny that the rest of the atom is a kind of quiet, open expanse. You are, in a very real sense, made of empty space. The bed you lie on is made of empty space. The air you breathe is made of empty space, with just a few tiny nuclei and electrons scattered through it. There is something soothing about that, something that invites you to let go of tension, to stop holding on so tightly to the idea of solidity. The world is not as hard as it seems. Rutherford published the results of the gold foil experiment in a paper in 1911. The paper was titled The Scattering of Alpha and Beta Particles by Matter and the Structure of the Atom. It was a careful, measured document, full of data and calculations, but its conclusion was clear. The atom had a nucleus. The nucleus was tiny, dense, and positively charged. The electrons were outside, at a great distance. The old plum pudding model was set aside, and the nuclear model took its place. This is a good place to pause, to let the image of the empty atom settle into your mind. The fly in the cathedral, the artillery shell bouncing off tissue paper, the dark room with the zinc sulfide screen, the young men counting flashes, the grey Manchester sky outside the window. All of these images are part of the same story, the story of how we learned that the world is not what it seems, that solid things are made of empty space, that the real substance of matter is concentrated in tiny, hidden centers that we are only just beginning to understand. Let the atoms around you become transparent now, in your imagination. Let the walls dissolve into vast open spaces, with a few tiny nuclei floating in them. Let the bed become a cloud of particles, held together by invisible forces, but mostly hollow. Let your own body become a constellation of tiny, dense points, surrounded by emptiness. There is nothing to fear in this. It is simply how things are. It has always been how things are. And now you can rest in that knowledge, floating in the empty spaces between nuclei, drifting through the vast interior of the atom, like an alpha particle passing through gold foil, unbent, undeflected, moving softly through the void. The next step in our story will be to look more closely at the nucleus itself. Rutherford had discovered it. Now he was going to name its first piece. The proton was about to be identified, the first nuclear building block, the thing that makes one element different from another. But that is for later. For now, let the emptiness be enough. Let the silence and the darkness and the vast interior spaces of the atom be your companions as you drift toward sleep. The fly in the cathedral, the shell and the tissue paper, the quiet counting in the dark. Let it all fade now, slowly, gently, into the deeper darkness that waits beyond the glow of the screen. Rutherford had found the nucleus. Now he wanted to know what it was made of. The gold foil experiment had revealed that the nucleus was tiny and dense and positively charged. But what was that positive charge? Was it a single solid lump, or was it built from smaller pieces? And if it was built from smaller pieces, what were those pieces? The next clue came, as clues often do in science, from the simplest element. Hydrogen is the lightest element, the first one on the periodic table. A hydrogen atom is the smallest and simplest atom there is. It consists of a single electron orbiting a nucleus that is, in the most common form of hydrogen, just one particle. That particle carries a single unit of positive electric charge. It is the smallest positive charge that occurs naturally. Rutherford began to suspect that this hydrogen nucleus might be a fundamental building block, the basic unit of positive charge from which all other nuclei were built. He tested this idea by doing another experiment, this time firing alpha particles not at gold foil, but at nitrogen gas. Nitrogen is a heavier element, with more protons in its nucleus. When Rutherford bombarded nitrogen with alpha particles, something interesting happened. Occasionally, an alpha particle would strike a nitrogen nucleus and knock something out of it. That something, that fragment, was light and positively charged. When Rutherford measured its properties, he found that it was identical to the nucleus of a hydrogen atom. He had chipped a hydrogen nucleus out of a nitrogen nucleus. This suggested very strongly that hydrogen nuclei were present inside the nuclei of heavier elements. They were building blocks, components of the nucleus. Rutherford gave this particle a name. He called it the proton, from the Greek word protos, meaning first. The proton was the first nuclear particle to be named, the first piece of the nucleus to be identified. It was a small, heavy particle with a single positive electric charge. It had a mass about 1,836 times the mass of an electron, and it was, Rutherford proposed, a fundamental constituent of all atomic nuclei. Let us spend some time with the proton. It is a remarkable thing. Every proton in the universe is identical to every other proton. A proton from a hydrogen atom in a glass of water on Earth is exactly the same as a proton from a hydrogen atom in a star on the other side of the galaxy. They have the same mass, the same charge, the same size, the same behavior. If you have seen one proton, you have seen them all. And yet, the number of protons in a nucleus is what makes one element different from another. It is the proton count that defines the identity of an atom. This is a simple and beautiful idea. An atom with one proton is hydrogen. An atom with 2 protons is helium. An atom with 3 protons is lithium. An atom with 6 protons is carbon. An atom with 8 protons is oxygen. An atom with 26 protons is iron. An atom with 79 protons is gold. An atom with 92 protons is uranium. And so on, all the way up through the periodic table. Each element defined by the number of protons in its nucleus. Change that number, and you change the element. Add 1 proton to a carbon nucleus, which has 6 protons, and you get nitrogen, which has 7. Add another proton to nitrogen, and you get oxygen, which has 8. Remove a proton from gold, which has 79, and you get platinum, which has 78. The identity of an element is not a matter of its electrons, or its chemical behavior, or its color, or its melting point. It is a matter of the number of protons in its nucleus. That number is called the atomic number, and it is the fundamental organizing principle of the periodic table. Rutherford's identification of the proton was a major step forward. The nucleus now had a known component. It was made, at least in part, of protons. The positive charge of the nucleus came from the protons. The number of protons told you what element you were dealing with. It was a clean, orderly picture. But there was a problem. The problem was the mass. Protons have a certain mass, roughly the same for each one. If the nucleus were made only of protons, then the mass of a nucleus should be roughly equal to the mass of its protons. But this was not what physicists measured. For most elements, the mass of the nucleus was about twice what you would expect from the number of protons alone. A helium nucleus, for example, had 2 protons, so it should have a mass roughly equal to 2 protons. But its actual mass was about 4 times the mass of a single proton. A nitrogen nucleus had 7 protons, but its mass was about 14 times the mass of a proton. The numbers did not add up. This was a puzzle. Where was the extra mass coming from? One possibility was that the nucleus contained extra protons, but that these extra protons were somehow neutralized by electrons packed inside the nucleus alongside them. This was an idea that Rutherford himself considered, but it turned out to be wrong. The true explanation would require the discovery of another particle, one with roughly the same mass as a proton, but no electric charge at all. That particle was the neutron, and its discovery would complete the basic picture of the nucleus. But that is for the next section of our story. For now, let us stay with the proton. Let us appreciate its role as the defining feature of the elements. The number of protons in a nucleus is the atomic number, the number that tells you what an atom is. This is a fact worth repeating, because it is so central to the story we are telling. Change the proton count, and you have made a different element entirely. Add a proton to hydrogen, and you get helium. Add a proton to helium, and you get lithium. The entire diversity of the material world, the 90-something naturally occurring elements, and all their combinations, is built on this simple principle. Different numbers of protons, arranged in different configurations, produce all the different kinds of atoms there are. Think about that as you lie here in the dark. The air you are breathing is mostly nitrogen and oxygen. Nitrogen has 7 protons in its nucleus. Oxygen has 8. The difference between the gas that sustains you and the gas that makes up most of the atmosphere is a single proton per atom. The carbon in every living thing has 6 protons. The iron in your blood has 26. The calcium in your bones has 20. The sodium and potassium that make your nerves fire have 11 and 19, respectively. Everything you are, everything you touch, everything you see, is made of elements that differ from one another only in the number of protons in their nuclei. This is a restful kind of knowledge. The complexity of the world, the endless variety of substances and materials and living things, reduces down to a simple counting game. 1 proton, hydrogen; 2, helium; 3, lithium; 4, beryllium; 5, boron; 6, carbon; 7, nitrogen; 8, oxygen. And so on, step by step, up through the periodic table, each element 1 proton heavier than the last. The world is made of a few dozen different kinds of atoms, and they differ from one another in this one simple way. Rutherford did not discover all of this at once. The identification of the proton was a gradual process, worked out over several years, from about 1917 to 1919. Rutherford was still in Manchester, still running his laboratory, still directing his team of young researchers. The war was on, the First World War, and many of his students and colleagues were away, serving in various capacities. Rutherford himself was involved in war work, developing methods for detecting submarines. But he kept his research going as best he could, in the hours between his other duties. Science does not stop for wars. It slows down, it gets harder, it takes place in stolen moments and borrowed hours. But it continues. The discovery of the proton was announced in a series of papers, written in Rutherford's plain, direct style. He did not claim to have found the ultimate building block of all matter. He was too cautious for that. He simply reported what he had seen. When alpha particles hit nitrogen gas, they sometimes knocked out particles that were identical to hydrogen nuclei. These particles were positively charged and had about the same mass as a hydrogen nucleus. They were, he suggested, constituents of the nitrogen nucleus, and perhaps of all nuclei. The name proton came a little later, around 1920, and it stuck. With the proton, the picture of the atom became a little clearer. At the center was the nucleus, tiny and dense, made of protons. The number of protons determined the element. Outside the nucleus, at a great distance, orbited the electrons, one electron for each proton in a neutral atom. The positive charge of the protons balanced the negative charge of the electrons. The atom as a whole was neutral. The nucleus was the anchor, the heavy center around which the light electrons danced. But the picture was not complete. The mass problem remained. Nuclei were heavier than they should be if they contained only protons. There was something else in there, something that added mass without adding charge. The missing piece was the neutron, and its discovery was still more than a decade away. But the search was on. Physicists knew there was something they were not seeing. They knew the proton was not the whole story, and they knew that finding the missing piece would require new experiments, new instruments, new ways of looking at the nucleus. This is a good place to pause. We have come a long way, from Democritus to Dalton, from Becquerel to the Curies, from Rutherford's classification of alpha, beta, and gamma rays to his discovery of the nucleus, and now to the naming of the proton. The atom is no longer a solid, indivisible ball. It is a complex structure with a tiny heavy center and a vast outer region of electrons. The center is made, at least in part, of protons. The number of protons defines the element. This is a lot to know and a lot to rest with. But none of it needs to be held tightly in your mind. The facts are here, but they are not a burden. They are more like stones in a stream, smooth and cool, and you can let your attention drift over them without grasping any one of them. The proton is a small thing, smaller than anything you can imagine, but it is also a solid thing, a reliable thing, the same in every atom of a given element, the same everywhere in the universe. There is comfort in that sameness. The laws of physics do not change from place to place or from time to time. A proton is a proton is a proton, whether it is in the tip of your finger or in a star a billion light years away. Let that thought settle into the quiet of the room. The sameness of things, the reliability of the small, the way the universe builds all its variety from a few simple pieces. The proton is one of those pieces, the neutron is another, and we will meet it soon. But for now, the proton is enough. One positive charge, one unit of mass, one tiny, sturdy building block, repeated over and over, in different numbers, to make all the different elements there are. Let the counting drift through your mind if you like. 1 hydrogen, 2 helium, 3 lithium, 4 beryllium, 5 boron, 6 carbon. The element you are made of, the element of life. 7 nitrogen, 8 oxygen. The element you are breathing right now, in and out, slowly and steadily. Let the numbers fade, one by one, as you sink deeper into the pillow. The story will continue when you are ready. There is no hurry. There is only the quiet and the dark and the slow rhythm of your breath. The proton was a good beginning, but it was not the whole story. For more than a decade after Rutherford named the proton, physicists lived with a puzzle they could not quite solve. The puzzle was about mass. The mass of a nucleus did not match the number of protons it contained. A helium nucleus had 2 protons, but its mass was about 4 times the mass of a single proton. A nitrogen nucleus had 7 protons, but its mass was about 14 times the mass of a proton. The numbers were roughly double what they should have been. Something was adding mass without adding charge. Something was hiding in the nucleus, and no one could find it. The search for this hidden particle went on through the 1920s. It was a quiet search, conducted in laboratories across Europe, in Cambridge and Paris and Berlin. Physicists tried different approaches, different experiments, different ways of probing the nucleus. They fired alpha particles at various targets and measured what came out. They studied the radiation from different elements. They built cloud chambers, devices that made the tracks of charged particles visible as thin lines of fog, and they photographed those tracks and studied them for clues. And all the while, the missing particle remained missing. It was there. They were sure of it. But it left no trace. It did not ionize gases. It did not make tracks in cloud chambers. It passed through matter as though it were not there at all. If it existed, it was electrically neutral, and that neutrality made it nearly invisible. The person who finally found it was a quiet, reserved English physicist named James Chadwick. Chadwick had been a student of Rutherford's at Manchester, and he had followed him to Cambridge after the war. He was a careful, methodical experimenter, the kind of person who checked his measurements 3 times and then checked them again. He had been looking for the neutral particle for years. He had a hunch it was there, and he was patient enough to wait for the right experiment to come along. That experiment came in 1932, and it came from an unexpected direction. In Paris, the Joliot-Curies, Irène and Frédéric, were studying a new type of radiation. They were firing alpha particles at beryllium, a light metal, and they noticed that the beryllium gave off a very penetrating radiation. This radiation could knock protons out of paraffin wax, which is rich in hydrogen. The Joliot-Curies assumed the radiation was gamma rays, very energetic light. Gamma rays were known to be able to knock particles out of materials, so this was a reasonable guess. But Chadwick read their paper and had a different idea. He thought the radiation might not be gamma rays at all. He thought it might be a stream of neutral particles, particles with roughly the same mass as protons but no electric charge. Chadwick set out to test his idea. He repeated the Joliot-Curie experiment, but with a crucial difference. He measured the energies of the protons knocked out of the paraffin, and he did the same with other light atoms, like helium and nitrogen. He found that the energies made sense only if the incoming radiation was made of particles with a mass close to that of the proton. Gamma rays, which have no mass, could not account for the results. The particles had to have mass. They had to be something new. Chadwick had found the neutron. He announced the discovery in a paper published in the journal Nature in February of 1932. The paper was short, just a few pages, and it was written in the plain, understated style that Rutherford had taught him. He did not claim to have revolutionized physics. He simply laid out the evidence and let the conclusion speak for itself. There was a new particle. It had roughly the same mass as a proton. It had no electric charge. It was a constituent of atomic nuclei, and its existence solved the mass puzzle that had been troubling physicists for more than a decade. The neutron was the missing piece. A helium nucleus, for example, was not just 2 protons, it was 2 protons and 2 neutrons. That gave it a total of 4 heavy particles, which matched its mass. A nitrogen nucleus was not just 7 protons. It was 7 protons and 7 neutrons, 14 heavy particles in total. The mass problem was solved. The nucleus was made of protons and neutrons, bound together by a force that was not yet fully understood. The proton count gave the element its identity, its atomic number. The neutron count added mass without adding charge. Together, the protons and neutrons made up the nucleus, the tiny dense core at the center of every atom. Let us sit with the neutron for a while. It is a quiet particle, as particles go. It has no charge, so it does not announce itself with electric effects. It does not ionize atoms as it passes through matter. It does not bend in magnetic fields. It interacts with other particles only through the strong nuclear force, the force that holds the nucleus together, and through gravity, which is negligible at these tiny scales. A neutron can pass through a great deal of matter without being stopped or even noticed. It is, in a sense, the shy particle, the one that keeps to itself. But the neutron is also essential. Without neutrons, there would be no nuclei heavier than hydrogen. Protons repel each other electrically. 2 protons alone cannot stick together. The electric repulsion pushes them apart. Neutrons add no electric repulsion, but they do add the attractive force that holds the nucleus together. They act as a kind of glue, a buffer, a spacer that allows protons to crowd together without flying apart. Every nucleus heavier than hydrogen contains neutrons for this reason. The more protons a nucleus has, the more neutrons it needs to stay stable. Uranium, with its 92 protons, needs well over 100 neutrons to hold itself together. The discovery of the neutron completed the simple model of the atom. At the center was the nucleus. made of protons and neutrons. The number of protons determined the element. The number of neutrons could vary, even for the same element, giving rise to different versions of that element. These different versions are called isotopes. The word isotope comes from Greek roots meaning same place, because different isotopes of the same element occupy the same place on the periodic table. They have the same number of protons, so they are the same element, but they have different numbers of neutrons, so their masses are different. Isotopes are a gentle concept, and we can take our time with them. Most elements come in more than one form. Carbon, for example, has 6 protons, always. That is what makes it carbon. But a carbon atom can have 6 neutrons, or 7, or 8. Carbon with 6 neutrons is called carbon-12 because it has 12 heavy particles in total, 6 protons and 6 neutrons. Carbon with 7 neutrons is carbon-13. Carbon with 8 neutrons is carbon-14. All 3 are carbon. They all have 6 protons. They all behave chemically the same way. But carbon-14 is radioactive. It decays over time, while carbon-12 and carbon-13 are stable. This is the gentle variation that nature allows. Same element, different neutron count, slightly different personality. The same is true for many other elements. Hydrogen, the simplest element, has 1 proton. Most hydrogen atoms have no neutrons at all, but some have 1 neutron. This is called deuterium, or heavy hydrogen. A very few have 2 neutrons. This is called tritium, and it is radioactive. Oxygen has 8 protons, and usually 8 neutrons, giving oxygen-16, the most common form, but it also comes as oxygen-17 and oxygen-18, with 9 and 10 neutrons respectively. Uranium comes in 2 main forms. Uranium-238 has 92 protons and 146 neutrons. Uranium-235 has 92 protons and 143 neutrons. The difference of 3 neutrons matters a great deal, as we will see when we come to the story of fission. The concept of isotopes is a soothing one in its way. It is a reminder that nature allows small variations, small differences within a larger sameness. 2 atoms can be the same element, can behave the same way chemically, can occupy the same place in the grand order of things, and yet be slightly different inside. They can have a few more neutrons or a few fewer. They can be heavier or lighter. They can be stable or unstable. There is room, even at the smallest scales, for individuality. Chadwick's discovery of the neutron was the last major piece of the basic nuclear puzzle. After 1932, the atom had a clear structure, a nucleus of protons and neutrons, surrounded by electrons in orbit. The protons gave the charge, the neutrons gave the extra mass and the binding force. The electrons gave the chemical behavior. It was a complete, satisfying picture, and it opened the door to the next phase of the story, which was about what happens when you try to split that nucleus apart. Chadwick himself did not rest on his discovery. He continued to work, continued to study the properties of the neutron, continued to train students and write papers. He was, by all accounts, a gentle and modest man. He did not seek the spotlight. He did his work, published his results, and let others build on what he had found. The Nobel Prize in Physics for 1935 went to him for the discovery of the neutron, an honor he accepted with characteristic reserve. There is something restful about Chadwick's story. It is not a story of dramatic breakthroughs or sudden flashes of insight. It is a story of patient work, of careful measurements, of a willingness to keep looking for something that everyone else had given up on. The neutron had been hiding in plain sight for years. Other physicists had seen hints of it and misinterpreted them. Chadwick was the one who looked at the evidence and saw what it really meant. He was the one who put the pieces together, and he did it quietly, without fanfare, in the way that much good science is done. Now the nucleus was complete. Proton and neutron, side by side, bound together by the strong nuclear force. The periodic table made sense. The masses of the elements made sense. The different isotopes made sense. The atom was no longer a mystery. It was a known structure, with known parts, arranged in a known way. And the next question was obvious. If the nucleus was made of parts, could those parts be rearranged? Could a nucleus be split? Could one element be turned into another? The alchemists had dreamed of transmutation for centuries. Now, for the first time, it seemed like it might actually be possible. But that is a story for the next quiet section, the story of fission, of how physicists learned to split the atom. For now, let us rest with the neutron. Let us appreciate its quiet, neutral presence. It is the particle that asks for nothing, that makes no demands, that passes through the world without a trace. And yet it is essential. Without it, there would be no elements heavier than hydrogen. Without it, there would be no carbon, no oxygen, no iron, no gold. Without it, we would not be here, lying in the dark, listening to a story about tiny things. Think of the neutrons inside you now. Every atom in your body that is not hydrogen contains neutrons. They are nestled in the nuclei, side by side with the protons, holding everything together. They are silent. They are invisible. They do their work without any fuss. And they have been there for a very long time. Many of the neutrons in your body were forged in stars that exploded billions of years ago, spreading their elements across space. The neutrons have traveled all that way, through time and distance, to be here now, in this moment, in this room, in the quiet dark. Let that thought settle, the long journey of the small, the patience of particles, the way everything that matters is built from things that cannot be seen. The neutron is a good companion for sleep. It is calm and steady, and asks nothing of you. Let it carry you now, gently, toward the next part of the story, which will be here when you are ready. There is no hurry. The nucleus is complete. The pieces are in place, and you can rest in that completeness, in the quiet order of things, as the night goes on around you. With the neutron in place, the nucleus made sense. Protons and neutrons, packed tightly together, held by a force stronger than the electric repulsion that tried to push the protons apart. It was a tidy picture, a complete picture, and for a few years physicists explored it calmly, mapping out the different isotopes, measuring masses, filling in the details of the periodic table. But there was a question that followed naturally from this new understanding. If the nucleus was made of parts, could those parts be rearranged? Could a nucleus be broken into pieces? Could one element be turned into another, the way the alchemists had dreamed of doing for centuries? The answer came from Berlin, in the year 1938, at a time when the world outside the laboratory was growing dark. The political situation in Germany was worsening. Many scientists had already left, driven out by the policies of the Nazi regime. Those who remained worked under increasing pressure and scrutiny. It was not an easy time for careful, patient science. And yet, in the middle of all that, a discovery was made that would change the course of history. Otto Hahn was a chemist, a careful and methodical man who had been working with radioactive elements for decades. His colleague Fritz Strassmann was younger, also a chemist, also precise and thorough. They were studying what happens when uranium is bombarded with neutrons. This was a natural line of inquiry. Chadwick had discovered the neutron in 1932. Enrico Fermi, in Italy, had been firing neutrons at various elements and finding that they often became radioactive, capturing the neutron and changing into a different isotope or even a different element. It was a kind of alchemy, but real, verifiable, reproducible. One element could indeed be turned into another by adding or removing particles from its nucleus. Hahn and Strassmann were following up on Fermi's work. They were bombarding uranium, the heaviest naturally occurring element, with 92 protons, with neutrons. They expected to produce new elements, heavier than uranium, what were called transuranic elements. This was the logical outcome. A uranium nucleus, struck by a neutron, would absorb it and become a still heavier nucleus, which might then decay by emitting a beta particle and become an element with 93 protons, something not found in nature. This was the expected path. This was what everyone thought was happening. But Hahn and Strassmann were chemists, and they were very good at their job. They were not just measuring radiation, they were chemically separating the products of their bombardments, identifying the elements that appeared after the neutron irradiation, and what they found baffled them. Among the products, they identified barium. Barium is a light element, much lighter than uranium. It has 56 protons, a little more than half of uranium's 92. Finding barium in the products was like firing a large shell at a boulder and finding that the boulder had split into two roughly equal halves. It made no sense within the existing understanding of nuclear reactions. No one had ever seen anything like it. Hahn was so puzzled that he wrote to his former colleague Lise Meitner, a physicist with whom he had worked closely for many years. Meitner was not in Berlin anymore. She had fled Germany a few months earlier because she was of Jewish descent and her position had become untenable. She was living in Sweden, in exile, trying to continue her work with limited resources. She received Hahn's letter and read it with great interest. He described the barium finding, and he asked for her thoughts. He knew he had found something important, but he did not know what it meant. Meitner thought about the problem over the Christmas holiday of 1938. She was staying with friends on the Swedish coast, and her nephew Otto Frisch, also a physicist, came to visit. They went for a walk in the snow. Frisch was on skis. Meitner walked alongside him, and as they talked, they worked out the explanation for what Hahn and Strassmann had seen. The uranium nucleus, they realized, was not absorbing the neutron and becoming heavier. It was splitting. The neutron was causing the nucleus to become unstable, to stretch and wobble like a drop of liquid, and then to break into two roughly equal pieces. These pieces were the nuclei of lighter elements, like barium. The process released a huge amount of energy because the pieces were more tightly bound than the original uranium nucleus. The energy came from the rearrangement of the nucleus into a lower energy, more stable shape. Meitner and Frisch put this explanation into a paper. Frisch coined a name for the process. He called it fission, a word borrowed from biology, where it describes the division of a living cell into two daughter cells. Nuclear fission, the splitting of the nucleus. The atom had been divided. Let us sit with this for a moment. The splitting of the atom is often talked about in dramatic terms, as a great and terrible breakthrough, and it was a breakthrough, but the actual moment of discovery was quiet. A walk in the snow, a conversation between two people who had known each other for a long time, a letter from a friend and colleague asking for help with a puzzle, the pieces coming together, not in a flash of lightning, but in the slow, thoughtful way that scientific understanding often arrives. Meitner and Frisch published their paper in the journal Nature in early 1939. The news spread quickly through the physics community. Niels Bohr, the great Danish physicist, carried the news to America, where he was attending a conference. Scientists in laboratories around the world immediately began to replicate the experiment, to confirm the finding, to measure the energy released, and the energy was significant. A single fission event, the splitting of a single uranium nucleus, releases about 200 million electron volts of energy. That is a very small number in everyday terms, but it is enormous for a single atomic event. It is millions of times more energy than is released in a typical chemical reaction, like the burning of a single atom of carbon. The nucleus, it turned out, stored far more energy than anyone had imagined. The key to the process was the uranium isotope known as uranium-235. This isotope, which has 92 protons and 143 neutrons, is particularly susceptible to fission when struck by a slow-moving neutron. The neutron enters the nucleus, makes it unstable, and the nucleus splits. Uranium-238, the more common isotope with 3 more neutrons, is much less likely to fission. This difference, 3 neutrons out of more than 200, would turn out to be immensely important. But we are getting ahead of ourselves. For now, let us stay with the discovery itself. Hahn and Strassmann in their Berlin laboratory doing careful chemistry, Meitner and Frisch in the Swedish snow doing careful physics. The collaboration across distance, across borders, across the darkening political landscape of Europe. Science still happening, even in difficult times, because people were curious and patient and unwilling to let go of a puzzle. Hahn was awarded the Nobel Prize in Chemistry for the discovery of fission in 1944. Meitner was not included. This was widely seen as an oversight, and Meitner herself handled it with grace. She continued her work, continued to correspond with colleagues, continued to be a respected figure in physics until her death in 1968. The exclusion of Meitner from the Nobel Prize is a part of the story, and it is worth noting quietly, without anger. History is full of such oversights. The science itself is larger than the awards. The discovery of fission was a turning point. Before 1938, the nucleus was an object of study, a puzzle to be understood. After 1938, it was a source of power. The energy released in fission was not just a laboratory curiosity. It was enough, in principle, to build a bomb. It was also enough, in principle, to drive an engine, to boil water, to turn a turbine, to light a city. The atom had moved from the realm of pure science into the realm of practical consequence. But the shift did not happen all at once. For a few months in early 1939, fission was still a scientific discovery, discussed at conferences and in journal articles. Physicists measured the energy released. They identified the fission products, the lighter elements that appeared after the split. They studied the neutrons that were emitted during fission, because it quickly became clear that a splitting uranium nucleus releases not just energy and fission products, but also more neutrons. 2 or 3 neutrons, on average, for each nucleus that splits. And those neutrons could go on to strike other uranium nuclei, causing them to fission in turn. The possibility of a chain reaction, a self-sustaining cascade of fissions, was apparent almost immediately. This is a concept that we will explore more in the next section. For now, let us stay with the quiet of the discovery itself. The barium in the chemical sample, the letter from Hahn to Meitner, the walk in the snow, the naming of fission. These are the small moments from which large consequences grow, and they are restful moments, if we let them be. They are moments of clarity, of understanding, of pieces falling into place. Think of the uranium nucleus, heavy and unstable, sitting at the top of a long slope. It has been there for a very long time, perhaps since the Earth was formed, perhaps since a star exploded somewhere in the galaxy and scattered its heavy elements across space. The uranium atom found its way into the Earth's crust, into a vein of ore, into a laboratory in Berlin. And there, in 1938, a neutron found it. A tiny, neutral particle, no bigger than the protons and neutrons already in the nucleus, slipped in and upset the balance. The nucleus wobbled, stretched, and broke. It fell apart into 2 smaller nuclei, releasing energy that had been stored since the star that made it. The energy radiated away as heat and light. The fission products, barium and krypton and strontium and others, scattered into the surrounding material, and a few new neutrons flew out, ready to find other nuclei, ready to continue the process. It is a quiet image, if you let it be, a tiny event, far below the threshold of human senses. No sound, no flash visible to the naked eye, just a rearrangement of particles, a settling into a lower energy state. The kind of thing that happens all the time, in the natural world, in the rocks beneath our feet, in the decay of radioactive elements. Fission, it turns out, occurs naturally in uranium deposits. It is not something that humans invented, it is something we discovered, something that has been happening quietly, on a very small scale, for billions of years. The difference, after 1938, was that humans now knew how to make it happen on purpose. We had learned to split the atom, and that knowledge would lead, in just a few years, to the fires over Hiroshima and Nagasaki, and to the controlled chain reactions of nuclear power plants, and to the long, slow debates about energy and safety and the future of the planet. The story was no longer just a story about tiny things and patient people. It had become a story about the world. But we are not there yet. We are still in Berlin, in the winter of 1938. Hahn and Strassmann are looking at their data, puzzled but careful. Meitner and Frisch are walking in the snow, working out the explanation. The word fission has just been coined. The news is about to spread. And for a brief moment, before the world changes, there is just the science. The quiet, patient, careful science. The satisfaction of a puzzle solved. The opening of a new door. Let that be the image that carries you forward into sleep. A snowy path in Sweden. Two people walking and talking. The crunch of snow under boots and skis. The cold air, the gray sky, the low winter light. And the slow dawning of understanding. The pieces fitting together, the atom revealing its deepest secret. There is no urgency in this image. There is only thought and conversation and the quiet pleasure of figuring something out. Let it settle over you like a blanket, soft and warm, as the story pauses and the night continues. The next chapter will come when you are ready. For now, there is only the snow and the quiet and the slow drift toward rest. The discovery of fission changed the mood of physics. Before 1939, the nucleus was a subject of quiet study, a puzzle for patient people in university laboratories. After the discovery, it became something else. It became a practical question. If a single splitting nucleus released energy, and if that splitting also released neutrons, and if those neutrons could split more nuclei, then a self-sustaining reaction was possible, a chain reaction. One split leading to two, two to four, four to eight, and so on, each step releasing a burst of energy until the whole thing ran out of fuel or was deliberately stopped. The idea of a chain reaction was not entirely new. A Hungarian physicist named Leo Szilard had thought about it years earlier, in 1933, standing on a street corner in London waiting for a traffic light to change. He had been reading about Rutherford's work, and the idea had come to him, the possibility that if you found an atom that could be split by a neutron, and if it released more than one neutron when it split, you could create a cascade. He had even filed a patent on the idea, assigning it to the British Admiralty to keep it secret. But in 1933, there was no known way to split an atom. Fission had not yet been discovered. The patent was an idea in search of a mechanism. Now, in early 1939, the mechanism had been found. The splitting of uranium released neutrons. On average, between 2 and 3 neutrons per fission. Those neutrons, if they hit other uranium nuclei, could cause more fissions. The chain reaction that Szilard had imagined was not just a possibility, it was, in principle, achievable. The question was whether anyone could actually make it work. The practical problems were significant. Natural uranium is mostly uranium-238, which does not fission easily. Only the rare isotope uranium-235, which makes up less than 1% of natural uranium, fissions readily with slow neutrons. To get a chain reaction going, you needed either to separate the uranium-235 from the uranium-238, a massive industrial undertaking, or you needed to slow the neutrons down so that they were more likely to cause fission in uranium-235 before they were absorbed by uranium-238. Slowing neutrons down required a material called a moderator, something light that neutrons could bounce off without being absorbed. Water was one possibility. Graphite, a pure form of carbon, was another. These were engineering problems, not just physics problems. And they were being considered in a world that was sliding toward war. In September of 1939, Germany invaded Poland. The Second World War had begun. Many of the physicists who had been studying fission were now in different countries, separated by borders and armies and the chaos of the time. The question of whether a chain reaction could be achieved was no longer just a scientific curiosity. It had military implications. A bomb based on a chain reaction would release energy on a scale that no chemical explosive could match. The governments of the world began to take notice. In the United States, a group of physicists, many of them refugees from Europe, were deeply concerned. Szilard was there, Eugene Wigner was there, Edward Teller was there, and they were worried that Germany, which had started the research on fission, might be working on a nuclear weapon. They persuaded Albert Einstein, the most famous scientist in the world, to write a letter to President Franklin Roosevelt, warning him of the possibility and urging the United States to begin its own research program. The letter was delivered in October of 1939. It set in motion a chain of events that would lead, eventually, to the Manhattan Project. The first step, though, was to prove that a chain reaction was possible. That proof came in December of 1942, in a squash court under the stands of an unused football stadium at the University of Chicago. The team was led by Enrico Fermi, the Italian physicist who had been studying neutrons for years and who had won the Nobel Prize in 1938 for his work. Fermi had left Italy with his Jewish wife to escape the racial laws of the fascist government. He had come to America, and he was now at the center of the effort to build the first nuclear reactor. The reactor was called Chicago Pile 1, or CP1 for short. The word pile was a leftover from the early days, when the idea was literally to pile up uranium and graphite in alternating layers. The pile was a rough, stacked structure, built by hand over several weeks. It contained about 45 tons of uranium oxide and uranium metal, and about 380 tons of graphite, stacked in a precise arrangement. It had no shielding, it had no cooling system. It was built in the middle of a city, under a stadium, surrounded by laboratories and classrooms and homes. The fact that it was safe to build it there tells you something about the carefulness of Fermi's approach. He knew exactly what he was doing. On December 2, 1942, the team gathered for the final test. They had been building up to this for weeks, adding layers to the pile, measuring the neutron activity, extrapolating to the point where the chain reaction would become self-sustaining. That point was called criticality. Below criticality, the reaction would die out. At criticality, it would continue at a steady rate. Above criticality, it would grow. The goal was to reach exactly criticality, to hold it there for a while, and then to shut it down in a controlled way. The control mechanism was simple. Cadmium strips, mounted on wooden rods, were inserted into the pile. Cadmium is a strong absorber of neutrons. With the rods fully inserted, the pile was subcritical. No chain reaction. As the rods were withdrawn, the pile approached criticality. Fermi directed the withdrawal, step by careful step, watching the neutron counters, doing calculations in his head. He was known for his ability to estimate things quickly and accurately, a skill that was on full display that day. The rods were pulled out in stages. The neutron counts rose. The critical point was approached. Finally, at 3:25 in the afternoon, Fermi gave the order to withdraw the last control rod a final distance. The pile went critical. The chain reaction was self-sustaining. It produced about half a watt of power at first, barely enough to light a small bulb. It ran for 28 minutes. Then Fermi ordered the control rods reinserted, and the reaction stopped. The first controlled nuclear chain reaction had been achieved. The atomic age had begun, quietly, under a football stadium in Chicago, in the middle of a war, in the middle of a city, in the middle of an ordinary afternoon. Let us sit with that scene for a moment. It was a cold December day. The squash court was unheated. The graphite dust was everywhere, black and greasy, coating the workers' hands and faces. The pile was a strange, lumpy structure, built of black bricks and wooden timbers, looking more like a rough piece of industrial equipment than a scientific instrument. Fermi stood on a balcony overlooking the pile, calm and focused, giving his orders in a steady voice. Around him, a small group of scientists and technicians watched the instruments. There was no applause when the pile went critical. There was a quiet sense of achievement, and then a quiet sense of what came next. One of the people present was Arthur Compton, the head of the Chicago laboratory. After the test was over, Compton called James Conant, the head of the National Defense Research Committee, to tell him the news. The call was cryptic, for security reasons. "The Italian navigator has landed in the New World," Compton said. Compton asked, "How were the natives?" Compton replied, "Very friendly." That coded exchange marked the moment. A chain reaction had been proven possible. The energy locked in the nucleus could be released in a controlled way, or in an uncontrolled way. The path to a bomb was now open. The path to a power plant was also open, but that would come later. For now, the war was the focus. The Manhattan Project was the name given to the enormous, secret effort to build an atomic bomb. It was a collaboration of unprecedented scale, bringing together scientists from many countries, engineers from many industries, and resources from across the United States. The project was directed by General Leslie Groves, a no-nonsense Army officer who had just finished overseeing the construction of the Pentagon. The scientific direction was under J. Robert Oppenheimer, a theoretical physicist of great talent and complexity. The main laboratory was built at Los Alamos, in the desert of New Mexico, on a mesa that had once been the site of a boys' school. The work was conducted in secrecy, behind fences and guard posts, with mail censored and telephones monitored, and families kept in the dark about what their loved ones were doing. The project had two main technical challenges. One was to produce enough fissile material, either enriched uranium with a high concentration of uranium-235, or a new element called plutonium, which could be produced in a reactor and also undergoes fission. The other challenge was to design a device that would assemble a critical mass of this material very quickly, fast enough to produce a nuclear explosion rather than a fizzle. Both challenges were met through a combination of brilliant physics, massive engineering, and a great deal of money and effort. The first test of an atomic bomb took place on July 16, 1945, in the desert near Alamogordo, New Mexico. The test was called Trinity. The bomb was a plutonium device, placed on a steel tower. At 5:29 in the morning, it was detonated. The light was brighter than the sun. The heat was felt miles away. The shock wave traveled through the desert air. A mushroom cloud rose into the stratosphere. The atomic age had moved from the laboratory to the world. 3 weeks later, on August 6, 1945, a uranium bomb was dropped on the city of Hiroshima, in Japan. On August 9th, a plutonium bomb was dropped on Nagasaki. The two bombings together killed more than 100,000 people, and perhaps as many as 200,000, many of them civilians. The war ended shortly afterward. Japan surrendered on August 15th. The bombs had done what they were designed to do. The cost in human life was immense. These are the facts, stated plainly. They are part of the history of nuclear physics, and they cannot be left out of any honest telling of the story. They are also difficult facts, heavy facts, and they sit uneasily alongside the quiet, patient discoveries that came before. How to hold these things together, the beauty of the science and the weight of its consequences, is a question that has no easy answer. The scientists who worked on the bomb grappled with it for the rest of their lives. Some felt they had done a necessary thing, ending a terrible war. Some felt they had opened a door that should have remained closed. Most felt a mixture of both, a complicated knot of pride and regret and uncertainty. We do not need to resolve this tonight. We are here to rest, not to judge. The history is what it is. The people who made these choices are gone now, and we are left with the world they helped create, a world in which nuclear weapons exist and have not been used in war since 1945. That is a kind of restraint, a kind of quiet that is worth noting. The chain reaction, as a concept, is a powerful one. One neutron starts it, 2 or 3 are released. Those go on to cause more fissions. The process multiplies, each step feeding the next. It is a cascade, an exponential growth, a thing that starts small and becomes enormous in a very short time. That is how a bomb works. That is also how a reactor works, when it is carefully controlled. The same physics, the same fundamental process, can be used to destroy a city or to light one. The difference is not in the physics, it is in the human choices that surround the physics. It is in the care, the control, the intention. Let us end this section by returning to the quiet of that squash court in Chicago. Fermi and his team, standing in the gray December light, watching the neutron counters, bringing the world's first reactor to criticality, and then shutting it down. They had done something new. They had tapped into a source of energy that had been locked inside the atom since the beginning of time. They had proven that a chain reaction was possible. What came next was not entirely up to them. The war, the government, the military, the vast machinery of history took over. But for that one afternoon, in that cold squash court, there was just the physics, the steady rise of the neutron count, the calm voice of Fermi giving orders, the quiet satisfaction of a problem solved. That is the image to hold on to as you drift. The squash court under the stadium, the graphite dust on the floor, the cold air and the gray sky outside, and the small, steady chain reaction, running for 28 minutes, producing half a watt of power, the first of its kind, the beginning of something new. Let it fade slowly now, the neutron counts dropping, the control rods sliding back into place, the pile going subcritical again. The story is not over. There is more to tell, about reactors and fusion and the particles inside particles. But for now, let the quiet return. The chain reaction has been stopped. The energy has been contained, and you can rest. The bombs fell, and the war ended, and the world had to decide what to do with the knowledge it had gained. The same chain reaction that had destroyed 2 cities could also, if controlled carefully, produce heat. Heat could boil water. Boiling water could make steam. Steam could turn a turbine could drive a generator, and a generator could produce electricity. The physics of the nucleus, which had begun as a quiet curiosity in Becquerel's drawer and had grown into a weapon of terrible power, could also become something else. It could become infrastructure. It could become a way to light homes and power factories and run hospitals and schools. It could become, in short, a nuclear reactor. The basic idea of a reactor is simple, and it has not changed much since Fermi's pile under the Chicago Stadium. You take a quantity of fissile material, usually uranium enriched to have a higher proportion of uranium-235 than natural uranium, or sometimes plutonium produced in other reactors. You arrange this material so that the neutrons from each fission can find other nuclei to split, keeping the chain reaction going. You insert control rods made of a material that absorbs neutrons, like cadmium or boron. When the rods are fully inserted, they soak up so many neutrons that the chain reaction stops. When you withdraw the rods gradually, the reaction starts and grows. You find the point where the reaction is exactly self-sustaining, exactly critical, and you hold it there. The reaction produces heat. You use a fluid, usually water, to carry the heat away from the reactor core. The hot water or steam then goes through a heat exchanger and boils more water into steam, which turns a turbine. The turbine spins a generator. The generator makes electricity. This is the same basic principle that coal-fired power plants use, and natural gas plants, and oil plants. They all boil water to make steam to turn a turbine. The difference is the source of the heat. In a coal plant, the heat comes from burning coal. In a nuclear plant, the heat comes from splitting atoms. The rest of the process is familiar engineering, pipes and turbines and cooling towers, the kind of thing that had been built and refined for more than a century. The physics of the nucleus, in this context, became just another way to boil water. The first nuclear power plant to supply electricity to a public grid was built in the Soviet Union, in a town called Obninsk, about 100 kilometers southwest of Moscow. It began operation on June 27, 1954. It was a small plant, producing about 5 megawatts of electricity, enough to power a few thousand homes. It was not a commercial venture in the way we think of today. It was a demonstration, a proof of concept. It showed that a nuclear reactor could be connected to a grid, could generate power steadily and reliably, could be operated by trained engineers, could become part of the ordinary infrastructure of modern life. The Obninsk reactor was a graphite-moderated, water-cooled design. The graphite slowed the neutrons. The water carried away the heat. The control rods kept the reaction steady. It ran for many years, long past its expected lifetime, and it trained a generation of Soviet nuclear engineers. It was decommissioned in 2002, after nearly 50 years of service. Today it is a museum, a quiet monument to the early days of civilian nuclear power. After Obninsk, other countries followed. The United Kingdom built Calder Hall, which began operation in 1956. The United States built Shippingport in Pennsylvania, which began operation in 1957. France began its nuclear program, which would eventually become one of the largest in the world, supplying more than 70% of the country's electricity. Japan, Germany, Canada, Sweden, and many other nations built reactors. Nuclear power grew from a handful of experimental machines to a global industry, with hundreds of reactors operating around the world by the end of the 20th century. The growth was not always smooth. There were debates about safety, about waste, about cost. There were accidents, some small and contained, some larger and more serious. 3 Mile Island in 1979, Chernobyl in 1986, Fukushima in 2011. Each accident taught lessons, led to new safety measures, new regulations, new ways of thinking about risk. The story of nuclear power is not a simple story of progress. It is a story of learning, sometimes the hard way, how to handle a source of energy that demands respect and carefulness. But we are not here to dwell on the accidents tonight. We are here to understand the reactor itself, the quiet heart of the process. A reactor is, at its core, a remarkably simple thing: a pile of fuel, a moderator, control rods, coolant, a way to get the heat out. The complexity comes from the safety systems, the backup upon backup upon backup that modern reactors are wrapped in. But the physics is the same physics that Fermi demonstrated in 1942, a chain reaction held at the edge of criticality, producing steady heat. Let us spend some time with the control rods, because they are a good example of how carefulness is built into the design. A control rod is made of a material that absorbs neutrons very strongly. Cadmium is one, boron is another, hafnium is a third. When the rod is inserted into the reactor core, the neutrons that hit it are absorbed and disappear from the chain reaction. With enough rods inserted, the reaction cannot sustain itself. It shuts down. The rods are held by mechanisms that can release them quickly in an emergency. In many designs, they are held up by electromagnets. If the power fails, the magnets release, and the rods drop into the core by gravity. This is called a scram, a term that dates back to the early days of the Chicago pile, when a safety officer stood ready to cut a rope with an axe if something went wrong. Modern reactors have more sophisticated systems, but the principle is the same. The default state, the state the reactor goes to if anything fails, is off. The chain reaction stops. The heat production stops. This is called fail-safe design. It is one of the reasons that serious accidents have been rare, though when they do happen, they are serious indeed. The heat from a reactor does not stop immediately when the chain reaction stops. The fission products, the lighter elements left over from the splitting of uranium nuclei, are radioactive and continue to decay, producing heat. This is called decay heat. It is a fraction of the full operating power, but it is still significant, and it requires cooling for days or weeks after the reactor is shut down. Managing decay heat is one of the central challenges of reactor safety. It is a quiet reminder that even when the chain reaction is stopped, the nucleus is still doing its slow, patient work, settling into stability, one decay at a time. The fuel in a reactor does not last forever. Over time, the uranium-235 is used up. The fission products build up, some of which absorb neutrons and make it harder to keep the chain reaction going. Eventually, the fuel must be replaced. This is called refueling. The spent fuel is removed from the reactor and stored, usually in pools of water that cool it and shield the radiation. The spent fuel is still radioactive. It contains fission products with half-lives ranging from seconds to thousands of years. It also contains plutonium and other heavy elements that could be recycled into new fuel, though not all countries do this. The question of what to do with spent nuclear fuel over the long term is one of the open issues in nuclear power. It is a problem that has been studied extensively, and various solutions have been proposed, including deep geological repositories where the waste can be isolated for the tens of thousands of years it takes for its radioactivity to decline to safe levels. But the political and social questions around waste storage have been harder to solve than the technical ones. This is one of the places where the story of nuclear power is still being written. Despite these challenges, nuclear power has become a significant part of the world's energy mix. As of the early 21st century, about 10% of the world's electricity comes from nuclear reactors. In some countries, the percentage is much higher. France, as mentioned, gets more than 70% of its electricity from nuclear power. The United States has the largest number of reactors, though they produce a smaller share of its total electricity. China, India, and other countries have been building new reactors. The physics that began in Rutherford's laboratory and grew in Fermi's squash court has become a quiet, steady part of daily life for billions of people, though they may not think about it when they turn on a light or plug in a phone. The reactor is a calming image if you let it be. Think of the core, a carefully arranged lattice of fuel rods and control rods and coolant channels. The neutrons move through it, bouncing off moderator atoms, finding uranium nuclei, causing fissions. Each fission releases a tiny burst of heat, a few neutrons, and two lighter nuclei. The heat warms the coolant. The coolant flows through pipes to a steam generator. The steam turns the turbine. The turbine turns the generator. The generator sends electricity out into the grid, through transformers and transmission lines, to homes and offices and streetlights. All of this happens steadily, quietly, day and night, without flames or smoke or the roar of combustion. A nuclear plant, from the outside, is mostly silent. The cooling towers release plumes of water vapor, which drift slowly upward and dissolve into the sky. The reactor building itself is a solid concrete dome, designed to contain anything that might escape. Inside, the chain reaction ticks along at a steady rate, controlled by the positions of rods and the flow of coolant. It is a machine, like any other machine, built and maintained by people who have trained for years to do their jobs carefully. This is where physics quietly became infrastructure. The discoveries of Becquerel and the Curies, of Rutherford and Chadwick, of Hahn and Meitner and Fermi, have been absorbed into the fabric of modern civilization. The atom, which once seemed impossibly remote and abstract, now powers a significant fraction of the world's electricity. The tiny, dense nucleus that Rutherford found at the center of the gold atom is now split millions of times per second in reactors around the globe, each split releasing a small amount of heat that adds to the total. The cumulative effect of all those tiny splits is enough to light cities. There is something restful about this. The same physics that can be used for destruction can also be used for peaceful, steady, reliable work. The chain reaction, when controlled, is not a runaway cascade, but a slow, measured burn. The neutrons find their targets at a predictable rate. The heat is carried away by water. The turbines spin at a constant speed. The electricity flows out into the grid, day after day, year after year. It is a kind of quiet diligence, a kind of patience, that echoes the patience of the scientists who uncovered the secrets of the nucleus in the first place. And so the story comes, in a way, full circle. From Democritus wondering about the smallest pieces of matter, to Dalton measuring the weights of atoms, to Becquerel finding that uranium could fog a plate, to the Curies isolating radium, to Rutherford sorting the rays and finding the nucleus, to Chadwick finding the neutron, to Hahn and Meitner discovering fission, to Fermi building the first pile, to the engineers and technicians who now operate reactors all over the world. It has been a long, slow journey, full of careful work and patient thinking. The reactor is not the end of the story. There is more to tell about fusion and quarks and the deeper layers of matter. But the reactor is a good place to pause, a good place to rest. Imagine a reactor core at night. The control room is dimly lit, with panels of gauges and screens showing temperatures and neutron fluxes and coolant flow rates. A few operators sit at their stations, monitoring the readings, making small adjustments. The reactor has been running for months, steady and reliable. The chain reaction is exactly critical, each fission producing exactly one neutron that goes on to cause another fission, neither growing nor shrinking. The heat flows out through the pipes, the turbines hum. Outside, the cooling towers release their quiet plumes into the dark sky. The whole plant is a kind of slow, steady heartbeat, a pulse of energy that never stops. Let that image carry you forward now. The quiet hum of the turbine, the soft glow of the control room panels, the steady, patient work of splitting atoms, one by one by one. Let it fade slowly, like the lights dimming in a room at the end of a long day. The story will continue when you are ready. There is no hurry. The reactor is running steadily. Everything is in order, and you can rest. Fission is the splitting of a heavy nucleus into lighter pieces. It is one way to release nuclear energy. But there is another way, a process that is in a sense the opposite of fission. Instead of breaking large nuclei apart, you can join small nuclei together. This is called fusion, and it is the process that powers the sun. Fusion is a gentler word than fission in some ways. It sounds softer. And the process itself, in its natural setting, is a slow and steady one. The sun has been fusing hydrogen into helium for about 4.5 billion years. It will continue to do so for another 5 billion years or so before it exhausts its fuel and swells into a red giant and then fades into a white dwarf. That is a long, slow timescale, the kind that makes human history seem very brief. The sun does not hurry. It burns steadily, quietly, at a temperature of millions of degrees, deep in its core, where the pressure is immense and the density is greater than solid lead. The basic idea of fusion is simple. When two light nuclei come close enough together, they can stick to each other through the strong nuclear force, the same force that holds protons and neutrons together in a nucleus. When they stick, they form a heavier nucleus. And because of the way nuclear masses work, the new nucleus weighs slightly less than the sum of the two original nuclei. The missing mass is converted into energy, according to the equation that Einstein made famous. Energy equals mass times the speed of light squared. The amount of mass converted is small, but the speed of light is very large, and squaring it makes it enormous. So a tiny amount of mass becomes a significant amount of energy. The most common fusion reaction in the sun is the joining of hydrogen nuclei to make helium. This happens in several steps, which together are called the proton-proton chain. Two protons fuse. One of them turns into a neutron, emitting a particle called a positron, and a tiny, neutral particle called a neutrino. The result is a deuterium nucleus, which is heavy hydrogen. Another proton fuses with the deuterium to make a form of helium with two protons and one neutron. Two of those helium nuclei fuse to make a normal helium nucleus, with two protons and two neutrons, releasing two protons in the process. The net result is that 4 hydrogen nuclei, 4 protons, become one helium nucleus, plus energy, plus 2 neutrinos that fly away into space. This is the furnace that powers the sun. It is also the furnace that powers most of the other stars in the sky. When you look up at night, if you happen to be somewhere far from city lights, you are seeing the light from distant fusion reactors, each one burning hydrogen into helium in its core. The starlight that falls on your closed eyelids, if you are lying outside, has traveled across space for years or centuries or millennia, and it was born in a nuclear reaction deep inside a star. That is a restful thought. The same physics that we have been tracing through the history of atomic science, the same protons and neutrons and strong nuclear force, are operating in every point of light in the night sky. The understanding of how stars produce energy was worked out in the 1930s, around the same time that fission was being discovered on Earth. The main figure in this work was Hans Bethe, a German-born physicist who had moved to the United States. Bethe was a careful, methodical theorist, one of the great physicists of his generation. He worked out the details of the proton-proton chain, and also of another fusion cycle called the carbon-nitrogen-oxygen cycle, or CNO cycle, which operates in stars more massive than the Sun. His papers on stellar energy production were published in 1939, the same year that Meitner and Frisch published their paper on fission. It was a remarkable moment. In the space of a few months, physicists understood both how to split the heaviest nuclei and how to fuse the lightest ones. The two great nuclear processes were revealed at almost the same time. Bethe's work earned him the Nobel Prize in Physics in 1967, nearly 30 years after his original papers. He lived a long life, working well into his 90s, a quiet and respected figure in the world of physics. And he was one of those scientists whose career spanned the entire nuclear age, from the early days of quantum mechanics to the development of the bomb to the debates over nuclear power and nuclear arms control. Through it all, he remained calm and thoughtful, a voice of reason in a field that often provoked strong emotions. Fusion on Earth has been a goal for scientists and engineers since the 1950s. The idea is simple to state. If you can create conditions like the core of the Sun, extremely hot and dense, you can make hydrogen nuclei fuse and release energy. That energy could be used to heat water into steam and turn a turbine, just like a fission reactor or a coal plant. The fuel for fusion is abundant. Hydrogen is the most common element in the universe. Deuterium, the heavy form of hydrogen with one neutron, can be extracted from seawater. Tritium, the still heavier form with two neutrons, can be bred from lithium. There is enough fusion fuel on Earth to power human civilization for millions of years, if we can make it work. But making it work has proved very difficult. The problem is that fusion requires temperatures of tens or hundreds of millions of degrees. At those temperatures, the fuel is not a solid, not a liquid, not even a gas in the ordinary sense. It is a plasma, a state of matter in which electrons are stripped from their nuclei and everything moves at enormous speeds. A plasma is like a very hot, electrically charged soup. It is hard to confine. It wants to expand and cool. It cannot be held in a material container because any solid material would instantly vaporize on contact. So the plasma must be held in place by something else. The main approach to confining a fusion plasma is to use magnetic fields. A magnetic field can exert a force on charged particles, pushing them into a certain region of space. If you arrange the magnetic fields in the right way, you can create a kind of invisible bottle that holds the plasma in place. The most common design for this is called a tokamak, a Russian word formed from the first syllables of toroidal chamber with magnetic coils. A tokamak is a hollow donut-shaped chamber surrounded by powerful magnets. The plasma circulates inside the donut, held away from the walls by the magnetic fields. Electric currents and additional heating methods push the temperature up into the range where fusion can occur. Research into tokamaks has been going on since the 1960s. The Soviet Union was an early leader in the field, and the first tokamaks were built there. Other countries followed, building larger and more powerful machines. The Joint European Torus, or JET, in the United Kingdom, began operation in 1983 and has set records for fusion power production. The International Thermonuclear Experimental Reactor, or ITER, is currently under construction in southern France. It is a collaboration among 35 countries, the largest fusion experiment ever attempted. Its goal is not to generate electricity for the grid, but to demonstrate that a tokamak can produce more fusion energy than the energy required to heat and confine the plasma. That is the threshold known as energy-positive fusion, or sometimes called ignition. No fusion experiment has yet crossed that threshold in a sustained, controlled way. This is where the story of fusion becomes an unfinished one. Practical, energy-positive fusion power has not yet been achieved. It is not certain when it will be achieved, or whether it will ever become a commercially viable source of electricity. The challenges are immense. The materials that face the plasma must withstand intense heat and neutron bombardment. The plasma itself is difficult to keep stable. It tends to develop instabilities, wobbles, and kinks that can cause it to touch the walls and cool. The engineering of a fusion power plant, with its superconducting magnets and tritium-breeding blankets and heat exchangers, is enormously complex and expensive. It is possible that fusion will become a practical source of power within the next few decades. It is also possible that it will not. This uncertainty is simply part of where the science stands. It is not a failure, and it is not a reason for alarm. It is just the way things are. Some problems take a very long time to solve. Some problems may never be solved, or may be solved in ways we cannot yet imagine. The history of science is full of such open questions. They are not gaps to be feared. They are invitations to continued patience, continued carefulness, continued work. There are other approaches to fusion besides tokamaks. Some researchers are working on laser-driven fusion, in which powerful lasers compress and heat a small pellet of fusion fuel. The National Ignition Facility in the United States has pursued this approach. In December of 2022, they announced that they had achieved a fusion reaction that produced more energy than the laser energy delivered to the pellet, a significant milestone. But the total energy required to power the lasers was still far greater than the fusion energy output, so this was not yet a net gain in the practical sense. The work continues. Other concepts include stellarators, which are like tokamaks but with a more complex magnetic geometry, and various private companies pursuing smaller, more innovative designs. The field is active and progress is being made, but the destination remains somewhere ahead, not yet reached. Let this uncertainty sit calmly in the room. It is not a problem to be solved tonight. It is just another part of the long, slow story of the nucleus. We have learned to split heavy atoms. We have not yet learned to join light ones in a way that gives back more energy than we put in. The sun knows how to do it, but the sun has advantages we lack. It has immense gravity to confine its plasma. It has a volume that is, to put it mildly, larger than anything we can build, and it has been practicing for billions of years. We have been working on fusion for less than a century. It is all right that we have not yet succeeded. There is something restful about the idea of fusion, even in its unfinished state. The sun rises every morning. It burns its steady burn, fusing hydrogen into helium, sending out light and warmth. It does not ask anything of us. It does not care whether we ever master its secret. It simply shines. And we, here on Earth, continue to try, patiently, carefully, generation after generation, to bring a little piece of that stellar fire down to our level. It is a quiet ambition, pursued in laboratories and test facilities around the world, by people who know they may not live to see the final result. That kind of patience, that willingness to work on something that may not be finished in your lifetime, is one of the best things about science. It connects you to the past and to the future. It makes you part of a chain of effort that spans centuries. Think of the sun now, as you lie here in the dark. It is on the other side of the earth, presumably, unless you are sleeping during the day. But it is still there, still burning, still fusing. Deep in its core, the temperature is about 15 million degrees. The density is about 150 times the density of water. The protons move at enormous speeds, colliding, fusing, releasing energy. That energy works its way outward, through the layers of the sun, a journey that takes tens of thousands of years. Then it reaches the surface and flies out into space as light. 8 minutes later, it reaches Earth. It warms the air and the ground. It drives the weather, it feeds the plants. It is the ultimate source of almost all the energy we use, except for nuclear fission and geothermal heat. The sun is a fusion reactor, and we are its beneficiaries. Let that thought carry you now, toward the quieter parts of the night. The sun, burning steadily in the dark of space. The physicists, working patiently in their laboratories, trying to understand how it works and how to replicate it. The open questions, the unfinished projects, the long arcs of effort that span lifetimes. All of it is part of the same story, the story of the nucleus, the story of tiny things and patient people. Fusion is the other half of that story, the complement to fission, the joining instead of the splitting. And it is still being written. That is all right. Not everything needs to be finished. Not everything needs to be resolved. Some things can simply be in progress, moving slowly forward, like the light from a distant star traveling across the quiet dark. For a long time, the proton and the neutron were thought to be the smallest pieces of the nucleus. They were the fundamental particles, the indivisible units from which all matter was built. The word atom had once meant uncuttable. That turned out to be wrong. Atoms could be divided into nuclei and electrons. Then the nucleus turned out to be made of protons and neutrons, and for a while, it seemed as though the division might stop there. Protons and neutrons were simple, solid, elementary. They had no parts, they were the end of the line. But nature, as it often does, had more layers to reveal. In the middle decades of the 20th century, physicists began to suspect that protons and neutrons were not elementary after all. The clues came from experiments that smashed particles together at very high speeds, using machines called particle accelerators. These machines take protons or electrons and speed them up to enormous energies, then crash them into targets or into other beams of particles. When the particles collide, the energy of the collision can create new particles, some of which had never been seen before. By the 1950s and 60s, the number of new particles being discovered was growing rapidly. There were pions and kaons and lambdas and sigmas and x's and many others. The list became long and confusing. Physicists began to speak of a particle zoo, a phrase that captured both the variety and the disorder of the situation. There were too many particles. They did not fit into a simple scheme. The proton and the neutron, it seemed, were not alone. They were part of a much larger family, and the family relationships were not clear. A physicist named Murray Gell-Mann, working at the California Institute of Technology, was one of the people who began to bring order to this chaos. He noticed that the many particles could be grouped into families based on their properties. The patterns were suggestive. They implied that the particles were not elementary, but were made of smaller, more fundamental pieces. Gell-Mann called these pieces quarks. The name was a nonsense word, borrowed from a line in James Joyce's novel, Finnegan's Wake, 3 quarks for muster mark. Gell-Mann liked the sound of it, and the name stuck. At around the same time, a physicist named George Zweig, working at CERN in Switzerland, independently proposed a similar idea. He called his fundamental pieces aces, but Gell-Mann's name, quarks, was the one that caught on. The two men, working separately, had arrived at the same basic insight. Protons and neutrons are not elementary particles. They are made of smaller things. The theory of quarks is simple in its broad outlines, and we can describe it without getting lost in complexity. There are 6 kinds of quarks, or 6 flavors, as physicists call them. The flavors have names that are not meant to be taken literally. They are labels, just as alpha, beta, and gamma were labels for Rutherford's 3 kinds of radiation. The 6 quark flavors are up, down, charm, strange, top, and bottom. The up and down quarks are the lightest and most common. They are the ones that make up protons and neutrons. The other 4 flavors are heavier and less stable. They appear in high-energy collisions and in cosmic rays, but they do not make up ordinary matter. A proton is made of two up quarks and one down quark, held together by the strong nuclear force. A neutron is made of two down quarks and one up quark. The charges of the quarks add up to the charges of the proton and neutron. An up quark has a charge of plus 2/3. A down quark has a charge of minus 1/3. Two ups and a down give plus 2/3 plus 2/3 minus 1/3, which equals plus 1, the charge of the proton. Two downs and an up give minus 1/3 minus 1/3 plus 2/3, which equals 0, the charge of the neutron. The arithmetic is neat and satisfying. The force that holds quarks together is called the strong nuclear force, the same force that holds protons and neutrons together in the nucleus. But at the quark level, the strong force behaves in a particular way. It is carried by particles called gluons, which act as the glue between quarks. The gluons are massless, like photons, but unlike photons, which do not interact with each other, gluons interact with each other quite strongly. This makes the theory of quarks and gluons mathematically intricate, and it leads to a property called confinement. Confinement means that quarks cannot be isolated. You cannot pull a single quark out of a proton and study it by itself. If you try to pull quarks apart, the force between them grows stronger, not weaker, until the energy required to separate them is so great that new quarks are created out of the energy, and you end up with more particles, not a single free quark. Quarks are always found in groups, bound together into larger particles. This idea of confinement can be a restful one. The quarks are always together. They never exist alone. There is a kind of community at the deepest level of matter, a togetherness that cannot be broken. The quarks move within the proton, confined by the strong force, held in a small space, never free, but never alone either. They are always in relationship with each other, always interacting, always exchanging gluons. It is a dynamic, busy life at the smallest scales, but it is a life that is entirely contained, entirely stable, entirely predictable in its statistical behavior. Gell-Mann received the Nobel Prize in Physics in 1969 for his work on the classification of particles and the prediction of quarks. The evidence for quarks came from experiments at the Stanford Linear Accelerator Center, where electrons were fired at protons, and the way they scattered revealed the presence of smaller, point-like objects inside the proton. The experimenters, Jerome Friedman, Henry Kendall, and Richard Taylor, received the Nobel Prize in 1990. The discovery of the top quark, the last and heaviest of the 6 flavors, came in 1995 at the Fermi National Accelerator Laboratory near Chicago. The theory was confirmed, piece by piece, over decades of careful work. The discovery that protons and neutrons are made of quarks did not change the basic picture of the atom. The nucleus is still made of protons and neutrons. The protons and neutrons are still made of quarks. The electrons are still outside the nucleus, and they are still, as far as anyone can tell, truly elementary. They are not made of smaller pieces. They are point-like particles with no internal structure. The same is true of quarks as far as we know. They are point-like. They have no parts. But physics is a cautious science. We have thought things were elementary before, and we have been wrong. It is possible that quarks and electrons are made of still smaller things, vibrating strings or loops of energy, or something else entirely. At present, there is no experimental evidence for this. It is an open question, and that is all right. The not knowing is part of the calm. Let us sit with the idea of quarks for a while. They are small beyond small, so small that it is hard to find words for their smallness. A proton is about 100,000 times smaller than an atom. A quark is smaller still, perhaps 1,000th the size of a proton, perhaps infinitely small, a true mathematical point. The numbers become meaningless. What matters is the idea of layers. The atom, which Democritus imagined as the smallest possible piece of matter, has turned out to be a complex structure with layers within layers. The nucleus, the electrons, the protons and neutrons, the quarks and gluons. Each layer was discovered by patient people working over many years. Each layer was a surprise in its time. Each layer opened up new questions and new puzzles. There is something comforting about this layered structure. It means that the world is deep. It means that there is always more to discover, always another box inside the box. It means that our understanding is always partial, always provisional, always open to revision. That can feel unsettling, if you want certainty, but it can also feel relaxing. We do not have to have all the answers. The universe is larger and stranger and more intricate than we can fully grasp, and that is simply how it is. We are small creatures on a small planet, and we have learned to peer very deeply into the structure of matter, but we have not reached the bottom. We may never reach the bottom, and that is all right. Think of a proton, sitting in the nucleus of an atom somewhere inside your body. Inside the proton, two up quarks and a down quark are moving, exchanging gluons, held together by the strong force. They have been there since the proton was formed, which may have been in the first moments after the Big Bang, or may have been in a star that exploded billions of years ago. Protons are very stable. They do not decay as far as anyone can tell. They last for an immensely long time. The quarks inside them have been there, in their confined dance, for the entire history of the universe. They have never been alone. They have never been free. They have always been together in their small, tight space, moving in patterns that physicists can calculate with great precision, but can never directly see. The story of quarks is, in a way, the story of this whole long narrative in miniature. Someone noticed a pattern that did not make sense. Someone proposed a new idea, a new particle, a new layer. People were skeptical at first, and then the evidence came in, and the idea was accepted, and it became part of the standard understanding. The names were fanciful, but the mathematics was rigorous. The quarks were strange and charm, and top and bottom, but they were also real as the proton and the neutron and the electron. And now we live in a world where any child can learn about quarks, where the idea that protons are made of smaller pieces is taught in middle school science classes. The frontier of knowledge moves forward, and what was once strange becomes familiar, and what was once the subject of intense debate becomes settled fact. Gell-Mann was known as a brilliant and somewhat eccentric figure. He had wide interests in linguistics and archaeology and birdwatching. He was known for his precise way of speaking and his insistence on pronouncing foreign words correctly, even when it made him hard to understand. He was a person of immense intellectual confidence, and he was right about quarks. Zweig, the co-discoverer, had a quieter career. He eventually left particle physics and worked in neuroscience, studying how the inner ear converts sound into nerve signals. His aces did not catch on, but his insight was genuine. The history of science is full of such stories, of people who saw the same thing from different angles, of names that stuck and names that did not, of credit that was distributed unevenly. It is all part of the human side of the story, the side that involves personalities and careers, and the sometimes messy process by which knowledge is made. But the quarks themselves do not care about any of that. They continue their dance, inside every proton and neutron, inside every nucleus, inside every atom, inside everything. They are the deepest layer we have found so far, the smallest pieces we know, and they are content, if one can say such a thing, to be what they are. They do not strive, they do not hurry, they simply exist, moving in their confined space, held by forces that are both strong and subtle. They are a good image for the end of a long story. Small, contained, steady, and calm. Let the quarks settle in your mind now. Up, down, charm, strange, top, bottom. 6 flavors, 3 in a proton, 2 up and 1 down, 3 in a neutron, 2 down and 1 up. The gluons flashing back and forth, binding everything together. The strong force, the strongest force in nature, operating at the smallest scales, holding the smallest pieces in their tight embrace. It is a picture of quiet order, of deep structure, of the way the universe builds complexity from simplicity by layering one thing on top of another. We are nearly at the end of the story. There is one more section, a quiet close, a soft drifting off. But for now, let the quarks be the image you hold. Tiny, indivisible, point-like, confined. The smallest things we know, but not the end of the line, perhaps. There may be more layers. There may always be more layers. The search continues. But tonight, the search is not yours to carry. Tonight, you can let the quarks dance their quiet dance and think no further. The layers are there, the structure is solid, and you are held by it, as surely as the quarks are held by the strong force. Let that be enough. Let that be everything. The story is winding down, the night is deep, and you can rest. And so we come to the quiet close, the slow settling at the end of a long walk. We have traveled from ancient Greece to modern laboratories, from the first guesses about indivisible pieces to the discovery of quarks. It has been a journey of a little over a century, if we count from Becquerel's fogged photographic plate in 1896, or of more than 2,000 years, if we count from Democritus and his laughing philosophy. Either way, it has been a journey made by patient people, working carefully, step by step, across generations and continents, and the slow unfolding of time. Everything solid, including the body lying still right now, is mostly empty space. This is the central image, the one we keep returning to. Rutherford's gold foil, the alpha particles passing straight through, the vast empty interior of the atom with its tiny dense nucleus at the center, the fly in the cathedral, the artillery shell bouncing off tissue paper. The solid world is an illusion, a side effect of electric forces. Underneath that illusion, everything is made of almost nothing. Think of your own body lying here in the dark. The skin, the bones, the muscles, the blood. Each cell is made of molecules. Each molecule is made of atoms. Each atom is mostly empty, a tiny nucleus surrounded by a cloud of electrons. The nuclei themselves are made of protons and neutrons. The protons and neutrons are made of quarks, and the quarks, as far as we know, are point-like, without size, without internal structure. So your body, this solid, familiar thing that carries you through the world, is a collection of infinitesimal points separated by vast reaches of nothing. And yet it holds together. It breathes. It rests. It feels the weight of the blanket and the softness of the pillow. The forces that hold it together are strong enough to create the sensation of solidity, even though the underlying reality is one of almost perfect emptiness. This is not a thought to be troubled by. It is a thought to rest in. The emptiness inside you is not a void to fear. It is the same emptiness that fills the space between stars, the same emptiness through which light travels, the same emptiness that has been present since the beginning of time. It is quiet, and it is peaceful, and it is yours. You are made of stardust, as the saying goes, but you are also made of emptiness, and that emptiness is as much a part of you as the particles that float in it. The story we have told is a story of discovery, but it is also a story of patience. Becquerel waiting for the sun to come out, and finding something new in a closed drawer, the Curies stirring pots of pitchblende in a leaky shed, year after year, to isolate a fraction of a gram of radium, Rutherford counting alpha particles one by one in a darkened room, and realizing that a few of them were bouncing back. Chadwick searching for a neutral particle that everyone else had missed. Meitner walking in the snow, working out the explanation for fission. Fermi building a pile of graphite bricks under a football stadium, bringing the chain reaction to life, and then quietly shutting it down. Gell-Man looking at the particle zoo and seeing the patterns that meant quarks. All of these people worked slowly. They did not rush. They did not expect instant answers. They were content to move forward one small step at a time. That patience is something we can borrow, here in the dark. There is no need to hurry towards sleep. There is no need to force anything. The body knows how to fall asleep. It has been doing it since you were born. You can trust it, the way you can trust the steady burning of the sun, the slow decay of a radioactive nucleus, the quiet dance of quarks inside a proton. The processes that sustain the universe are patient processes. They unfold over timescales that make a human lifetime seem very brief. And yet we are part of them. We are made of the same stuff, governed by the same laws, embedded in the same vast, slow, patient flow of time. The story from ancient guesses to quarks took a little over a century of careful work, if we measure from the first experiments on radioactivity to the discovery of the top quark. It took much longer if we measure from Democritus, but in either case, it is a story that is still being written. There are open questions. There are things we do not yet understand. Fusion remains unfinished. The deeper structure of quarks and electrons, if there is one, remains unknown. There may be more layers. There may always be more layers. That is not a cause for worry. It is simply the way things are. The universe is larger and stranger than we can fully grasp, and it will still be there in the morning, full of questions, full of mysteries, full of invitations to patience and care. But you do not need to carry any of that tonight. The questions can wait. The mysteries can wait. Tonight is for letting go, for releasing the need to understand, for allowing the mind to settle into the simple fact of being here, in a body that is mostly empty space, on a planet that is mostly empty space, in a universe that is mostly empty space. The emptiness is not a lack. It is a kind of spaciousness, a kind of room to breathe. It is the space in which everything happens. It is the background, the container, the quiet field in which particles move and forces act and lives unfold. Let us return, one last time, to the image of Rutherford's gold foil. A thin sheet of gold, only a few hundred atoms thick, a beam of alpha particles streaming toward it, most of them passing straight through, as though the foil were not there at all. A few of them deflecting at small angles, a very few, perhaps one in several thousand, bouncing almost straight back. The empty atom, the tiny, dense nucleus, the revelation that solid matter is not solid at all. That was in 1909, in Manchester, in a laboratory that no longer exists in its original form. The building is gone, but the discovery remains. It is part of the permanent knowledge of humanity, a thing we now know about the world that we did not know before. Think of those alpha particles, passing through the gold foil. They were helium nuclei, clusters of 2 protons and 2 neutrons. They were fired from a small piece of radium, one of the elements the Curies had isolated with such difficulty. They traveled through the air, through the thin gold, and into the zinc sulfide screen, where they made tiny flashes of light. Geiger and Marsden sat in the dark and counted those flashes. They moved the screen around. They checked the far side of the foil, the side where nothing should have been, and they saw flashes there too, alpha particles bouncing back, the impossible result that turned out to be true. That image can be your companion as you drift. The alpha particles, heavy and fast, streaming through the emptiness of the gold atoms, most of them finding nothing, encountering nothing, passing through without any deflection at all. A few coming close to a nucleus and being nudged aside, a very few hitting almost head-on and being turned around. The nuclei of the gold atoms, tiny and massive, sitting quietly in their vast empty space. The electrons, light and quick, orbiting far away. The whole structure held together by forces that are invisible but powerful, electric forces and nuclear forces, the same forces that hold your body together right now. You are made of the same kind of atoms as the gold foil: carbon, oxygen, hydrogen, nitrogen, calcium, iron, and a scattering of other elements. Each atom is a miniature version of Rutherford's picture, a nucleus, tiny and dense, surrounded by electrons, held together by the same forces. The nuclei in your body are not gold nuclei, for the most part, but they are nuclei nonetheless, made of protons and neutrons, made of quarks, bound by the strong force. They have been there, many of them, for billions of years. They were formed in stars, in supernovae, in the slow cooking of elements that happens in the hearts of massive suns. They traveled across space. They became part of the earth. They became part of the food you eat, the water you drink, the air you breathe. They became part of you, and now they are lying here, in the dark, resting. There is a continuity to all of this, a long, unbroken chain of being that stretches back to the beginning of the universe. The quarks in your protons have been there since the first moments after the Big Bang, when the universe cooled enough for them to bind together. The hydrogen in your water was formed in that same early period. The heavier elements were formed later, in stars. The atoms in your body have been part of many things. They have been part of rocks and oceans and clouds and living creatures. They have been recycled, over and over, through the processes of geology and biology and chemistry. And now they are here, in this moment, in this quiet room, arranged in such a way that they can think and feel and listen to a voice in the dark. There is no need to remember any of this. The facts are not important, the names are not important, the dates are not important. What matters is the feeling, the sense of being part of something vast and old and patient. The sense that the same laws that govern the stars govern the beating of your heart, the sense that you are made of the same stuff as the rest of the universe, and that the emptiness inside you is the same emptiness that fills the spaces between galaxies. You are not separate from the world, you are a part of it, a temporary arrangement of particles and forces, a brief flowering of complexity in a universe that is mostly simple and quiet and dark. The story is over now, there is nothing more to tell. From ancient guesses to modern reactors, from Democritus to Gell-Mann, we have walked the path together, slowly, without hurry. You have listened, or perhaps you have drifted in and out of listening. Either way, the words have been here, a quiet presence in the dark, a voice to keep you company as you let go of the day. And now even the words are winding down. The sentences are getting shorter, the pauses are getting longer. The silence is growing, like a pool of dark water, still and deep and calm. Feel your breath, in and out, slowly and steadily. Your body knows how to do this. It has been breathing since the moment you were born. It will breathe all through the night, without any effort on your part. Let the breath be what it is. Let it come and go, like the tide, like the seasons, like the slow expansion and contraction of a star. Let it carry you. Feel the darkness around you. It is not empty. It is full of the same forces that hold the nucleus together, the same forces that keep the Earth in its orbit, the same forces that make the sun shine. The darkness is a kind of presence, a kind of holding, a kind of rest. You can trust it. You can let yourself fall into it, the way a pebble falls through still water, sinking slowly, turning gently, coming to rest on the sandy bottom. Everything is made of almost nothing. That is the truth we have been circling around, the truth we have been approaching from every angle, the truth that has been waiting for us at the end of the story. Everything solid is mostly empty space. Everything heavy is made of tiny, light particles. Everything permanent is in a state of slow, patient change. And yet, in the middle of all that emptiness and change, you are here, you are real, you are resting. The body knows how to do this. It has always known. So let the gold foil dissolve. Let the alpha particles stream through. Let the nuclei sit quietly in their vast cathedrals of space. Let the quarks dance their confined dance. Let the stars burn their slow burn. Let the universe continue its patient unfolding. You do not need to watch any of it. You do not need to hold any of it. You can let it all go now, gently, like a hand releasing its grip on the edge of a pool, letting the water take the weight. Breathe in, breathe out. The story is done. The night is here, and you can rest.